share my screen. Yeah, can you see my screen? Okay, thank you. So what is IDIES? And first, our mission is to support data-intensive science at Hopkins. And first of all, I would like to start off to say our thanks for two former members of our executive committee, Steve Salzberg and Nilanjan Chatterjee, and who have been with us for many years. And I would like to thank for all their help and contributions and efforts on behalf of IDIES. So we would simultaneously welcome 4 new members. So Paulette Clancy from the Whiting School has joined us, and she is in charge of the high performance computing, in particular, the Marcy and Arch. And so all the new high performance computing initiatives. Jeff Lee joined us from BSPH, from the Bloomberg School of Public Health, and he's in charge of our educational initiatives. Brian Caffo joined us from BSPH as the institutional representative from the Bloomberg School, and Alex Beres from the medical school became the new medical school representative. So I would like to talk about, what are all the ideas that IDIES would like to bring to Hopkins. So we would provide disruptive assistance, meaning that we would like to teach projects how to do these data-intensive projects on their own. So we are not here to actually serve as we are happy to consult, but we would like everybody to learn the new ways of dealing with big data in science. And we would like to institutionalize the lessons learned in a multidisciplinary setting. So we saw over the years that there are major key roles in which we can actually disrupt and help people starting new projects. These are the roles of the architects who help in a consulting role in translating basically the science challenges into the computational tools and implementations. We would have the implementers who would build the systems. And then we also see the roles of the so-called disruptors. So the faculty, once a data system, a new project is created with a large unique data set, then they actually come up with novel ideas. How can one use the existing tools to actually create new analysis patterns that nobody thought of before? We saw also over the years that the science engagements have distinctive phases of maturity. And so they go on from the conception of an idea all the way to public scale out. And this is actually not that dissimilar to the typical life cycle of startups. It is also clear that we need to have a critical mass of interdisciplinary postdocs and programmers. And the only way to support the projects with the multitude of skills that they need in terms of programming skills, scientific programming skills, is to have a pool of programmers who can spend a certain fraction of their time with the different projects. So we encourage everyone to think about these possibilities and work with us to actually establish a bigger and bigger pool of such programmers. I'm glad to say that we have several new people joining us over the next few weeks, our programming team. And Ani will actually discuss this a little tomorrow. So today we have more than 70 ongoing projects in various multidisciplinary engagements. We see altogether, we see a really nice and interesting convergence between physical sciences, life sciences, and social sciences. So we have projects from astronomy, turbulence, ocean circulations, material science, bioinformatics, hybrid brain-computer systems, quantitative social science, city planning, climate modeling, space weather, cryo-EM, cancer imaging. We are starting to work increasingly with beyond the borders of Hopkins, with national labs, federal agencies, the Max Planck Institute in Germany, with the National Observatory of Japan, with Rutherford Appleton. We are we have built innovative educational and outreach programs, in particular Jeff's engagements, Jeff Lee's engagements. So his Coursera classes had more than 7 million viewers. He built large national training networks, over 10,000 people, and the leading guiding philosophy is to train the trainers. This makes actually the whole effort scalable. And we would like to leverage our scalable and sustainable open infrastructure, which is currently well over 20 petabytes and more than 200 servers. And our data systems are used by over 7 million casual users, and we have more than 10,000 power users who have server-side databases, and more than 70 projects. A lot of it has been built with previous large NSF investment. And last but not least, we would like to create also a path for long-term sustainability. So the SciServer is at the center of a lot of these tools and utilities, and it's a scalable data aggregator. People have come to realize that it is quite difficult to aggregate large data sets because the joint analysis of multiple data sets are quite difficult if they are located at different parts of the planet. And so the joint analysis requires co-location. But one common mistake is when people try to aggregate data, they try to create the mother of all databases. So they try to tie up all the possible links between all these data sets as they bring the data in. And this creates actually a combinatorial problem. So if you already have 10 data sets and you want to bring in the 11th, you have to build links to all the other 10. And we have a very different philosophy. So we create actually data context, each with their own self-sufficient and closed data model and ontology, which is self-documenting. And these are secure and read-only under access control. And then the users get their own databases and resources to create their value-added aggregations and links between these data sets. So they have the total freedom to link these data sets whichever way they want. But such a way, adding a new data set is just a linear challenge. And then this can be shared and with groups of authenticated users at the owner's discretion. And such a way we can bring in new data sets very, very quickly at a linear cost. And we see basically the presence of big data as a crucial point in the future of bringing AI tools to the university, and see Gerard's presentations today about. So the lessons that we learned over the years that statistical analysis and collaboration is much easier with a database. Collaborative features are essential. We need to go beyond SQL scripting. So we brought in Jupyter and deep learning tool. Everything is spatial, from astronomy to cancer research and turbulence and oceans. In order to create statistical reproducibility, we need to automate the data ingest processes and the data processing. And as a result, scaling out is much harder than we ever thought. We learned not to try to do everything for everybody, but come up with the right trade-off. How can we build 20% of all the things that one can imagine that serves actually 80% of the user communities? We always need the deep links to the raw files because we need to able to figure out whether was there actually an instrumental glitch that is causing a certain phenomena. We need to find a common processing level that is good enough but very robust and earn the trust of the user community. And moving petabytes of data is hard, so there is an importance in doing smart data caching, to have the right data at the right place at the right time. And we are well along the path where we recognize certain usage patterns and what are the patterns in building new systems, and we are turning them into systematic processes. I'm happy to announce that our team was awarded the ACM Sigma Systems Award in 2021 for our work on the Sloan Sky Survey. And we are in an amazing company. So the previous year's teams in this is a database award. It's the Berkeley DB, which is Oracle. Then the Amazon's database. Then this is Facebook's database, the Hive and Pig. And in the previous years, there Mike Stonebreaker, who is of SciDB fame and also of Postgres. So this is the who is who in modern databases. So I would like to thank everyone who has been spending often many decades, several decades of their lives on making this long project successful. I would like to spend a minute on in memoriam Jan Vandenberg. Jan has been our main systems architect, and he started with our group in 1992 when he just was an undergraduate student at Hopkins, and he started to work with us part-time, and he then came in full-time to work with us, and he grew up literally at JHU and to become the senior architect. He has published many papers with very illustrious authors like Jim Gray and Gordon Bell of the Gordon Bell Prize fame, and Gordon has been the designer of all the DEC computers. He was part of the Data Challenge winning team on supercomputing 08. And all of that, beyond all of that, Jan was a wonderful colleague and a great friend. And we will greatly miss him. He was working until the very last minute at the end of a very, very difficult fight with cancer. So once again, let's hold just a second silence in his memory. And I would like to finish with the new projects and directions. So the Turbulence effort just received a new multi-institutional NSF grant, also support from a new institute within Hopkins. So this means that we are now reached the point of inflection. So we basically crossed this famous valley of death in startup language with Turbulence. So it is now really on a national growth path. We were awarded together with the University of Tennessee and the Ski Institute in Utah, a big NSF grant on the National Science Data Fabric, which is creating models for the new kind of scientific computing that we'll hear about with Ryan Abernathy's talk. Intel adopted Boba Braverman's load balancing technology. So we had a lot of successes in large-scale medical imaging. Janice will talk about our AstroFast project, which has recently won an award from a German foundation. And then there are many successful efforts in 3D imaging and spatial transcriptomics, which will become, I think, part of our everyday spectrum of things at Hopkins. We have new SciServer projects, and Judy will talk about how the SciServer is used at NIST. All of Hopkins is now preparing for a major concentrated effort in artificial intelligence, the AIX project, and Katie will talk about, its directions, why we are doing it and where we are heading. And one of the particularly interesting directions is in material science, and Rebecca Lindsay will talk about this. And we see lots of interesting new opportunities with a new Institute for Assured Autonomy led by Jim Bellingham, where the idea is to use AI to control not just self-driving cars, but use it also to control scientific experiments, to use AI in a new setting. So I would like to finish here and basically emphasize that the key to our success is constant innovation. And just recently I came across with a fortune cookie, which I thought was very appropriate. So I would like to end with that. So, finishing the introduction, let me stop screen sharing. And I have the pleasure to introduce our first keynote speaker. So Judy Mitrani-Reiser, who is the Associate Chief of Materials and Structural Systems Division at NIST. Judy is a member of the National Construction Safety Team for the technical investigation of Hurricane Maria's impacts on Puerto Rico and serves as the leader of the NCST project focused on characterizing the technical conditions associated with deaths and injuries. So prior to accepting her new position, Dr. Mitrani-Reiser served as the Director of Disasters and Failure Studies Program at NIST. She is currently also a Director of the Earthquake Engineering Research Institute. And Judy Mitrani-Reiser earned her bachelor's degree from the University of Florida, her master's from Berkeley, UC Berkeley, and her PhD from Caltech. And she has also been a professor at the Whiting School of Engineering at Johns Hopkins. So welcome back, Judy, to Hopkins.
Thank you so much. And thank you also, Alex, for the invitation to participate in this 2021 IDIES Symposium. So as Alex said, I have spent a lot of time on the Homewood campus, first as a postdoc and then later on as a professor. So it's truly an honor for me to return to this lovely community and to be able to share with you more recent work from our Materials and Structural Systems Division at NIST. And for those of you that I've never met before and have not had the pleasure to meet now in person, I hope we'll meet again someday soon at a conference or seminar, as we often did before the pandemic. So let me advance my slides. There we go. So extreme events test buildings and our infrastructure in ways and on a scale that cannot be replicated in a laboratory. Therefore, actual disasters and failure events provide really important opportunities for scientists and engineers at NIST and in other places to study these events so we can improve the safety of buildings and their occupants. So we've been studying disasters at NIST and failures for more than 50 years. The slide shows many of the events that NIST has studied or is currently studying under various authorities. And I've emphasized the word authorities because in the federal government, we don't do work unless we're authorized to do that work. So being authorized to do this type of work is really important to emphasize here. The items that I've highlighted in red are all of our NCST investigations, our National Construction Safety Team investigations, those that have been completed and some that are still active. The items that are in bold and in black are active research studies that are being conducted under other authorities. I'll describe a subset of these in just a little bit, but really the goal for NIST to take on such post-event assessments is to recommend improvements to building codes, standards, and practice that would make communities in the US more resilient to disasters. All right, this next slide shows an overview of the disaster resilience work that's undergoing at NIST. It also gives you a bit of insight into the structure of our organization, which can sometimes be a black box to those visiting our website. So let's start by describing some of our research programs, which are highlighted in blue. We have 4 research groups in the Materials and Structural Systems Division. The first is an infrastructure materials group that's focused on advancing the science of characterizing properties of materials that we use in our built environment, including buildings and distributed lifelines. We have a structural engineering group and an earthquake engineering group that have historically focused on characterizing building and structural system performance. Our newest group, not so new anymore, it's about 5 years old, but for NIST, it's pretty new. In our division is the Community Resilience Group. And this group is really focused on working on a wide range of, with a wide range of stakeholders to provide tools that help improve community resilience for all hazards, and with a focus on the built environment and the role that it plays in meeting social needs. We also house several of our statutory programs in our division, and those are programs that laws have been passed and are required for us to do at NIST. And so I'll describe some of these in just a moment as well. So I'm going to focus my talk today on disaster statutory programs. And the reason for that is those are the programs that have been under my purview at NIST for the last couple of years. So I'm going to start with the Disaster and Failure Studies program, which is actually the reason I left Hopkins was to direct this program. It's a program that coordinates all field studies at NIST, and that includes investigations by the National Construction Safety Team. So the NCST, or the National Construction Safety Team, is exactly the same as NTSB, but for buildings. So just like the National Transportation Safety Board is charged with making transportation in the US safer by conducting independent accident investigations and advocating for safety improvements, the NCST authorizes NIST to establish teams very similarly and assess building performance and emergency response and evacuation procedures in the wake of any building failure that has resulted in either a substantial loss of life or that pose significant potential for substantial loss of life. The NCST Act was passed in 2002, just after the World Trade Center towers collapsed. Attached to this law are some unique authorities for NIST. So some of those authorities are subpoena power, investigator badges, regular reporting to Congress by NIST and its associated Federal Advisory Committee, and also the responsibility of implementing any recommendations that are resulting from these investigations. So while NIST has the statutory authority to investigate structural failures and disasters and make recommendations, we have no regulatory authority at all. So we really do need to work cooperatively with government agencies at all levels and with the private sector and academia to implement some of the necessary changes to code standards and practice that we identify in these investigations. Now, this implementation phase can take a very long time, sometimes more than a decade. And this slide shows some of the impacts that our 3 completed NCST investigations have had on codes, standards, and practice. So we are currently have 2 open investigations, which is unusual for NIST. So in Puerto Rico, NIST is seeking to understand Hurricane Maria's impact, the wind environment, conditions that led to injuries and deaths, how critical buildings and design safe areas performed within them. And we are also looking at the dependency with electricity, water, and transportation and other infrastructure, which is unique to this type of investigation. We have a focus on emergency communication systems, how they performed, and the public's response to such communications, and the impacts to and recovery of selected businesses, hospitals, and schools. The team is investigating, so that's the left-hand side. On the right-hand side, we also have an active investigation due to the building collapse that occurred recently this summer. So the team that's investigating the collapse of the Champlain Tower South in Surfside, Florida, will establish the likely technical causes of the building failure, will recommend as necessary specific improvements to building standards, codes, and practices, and will also recommend any research and other appropriate actions that are needed to improve the structural safety of buildings. So I'm going to go into each of these in a bit more detail and just describe the projects that we are pursuing under each of these investigations. So first, under Hurricane Maria, central to understanding the impacts of Hurricane Maria on Puerto Rico is the study of the hazard itself. The hazard characterization project is using the Neary Wind Tunnel facility at the University of Florida, that's my alma mater, to characterize topographic speed-up effects and to validate numerical models. The project will also obtain full-scale measurements of winds in regions of topographic interest in Puerto Rico to help provide information that will validate our wind tunnel tests and also validate our numerical models. We have a second project that's focused on the performance of critical buildings. And really the emphasis on this project is to characterize the performance of hospitals and school buildings and shelters on the island. And we focus on these types of facilities because for the most part, these were designed based on building codes. And there's a lot of informal construction outside of critical facilities. So it'd be very challenging to recommend improvements to codes when we don't know what the starting place is or the baseline is for the building itself. So key to every NCST investigation is an understanding of human behavior and how it's associated with the building collapse. So the third project under our Hurricane Maria investigation investigates the role of emergency communications in public response for those imminent threat to the storm. So this project wants to identify the types of information that the public trusts. We're querying the public and trying to understand what news sources they look to for information and how it informed their decisions to take protective actions. The last project is one that I lead, and it's focused on the mortalities that resulted due to the storm. So death certificates greatly underestimate, we know this, they greatly underestimate deaths that are caused by disaster events, yet we heavily rely on death certificates and death tolls for the most part to characterize the impacts of disasters. So truly the objective of this project is to better understand how damaged buildings and its supporting infrastructure played a role in the injuries and deaths associated with Hurricane Maria. So now I'm going to switch gears to our second investigation that is active and was launched in late June. So within 48 hours of the Champlain Tower South collapse that occurred on June 24th, NIST staff began arriving on the site. We stayed continuously on the site for more than 2 months, collecting and documenting evidence for our investigation. We always approach our work with an open mind and with no preconceived notions. We're investigating all potential hypotheses that could explain what happened and led to this tragic collapse. With any building collapse, we want to understand how the building was designed, how it was constructed, modified, and maintained. We also want to know the condition of the building and its materials at the time of collapse. We need to desperately understand the geologic characteristics underneath the collapsed building site, as well as the properties of the building's foundation systems. I'm leading this investigative effort at NIST, and along with my co-lead, Glenn Bell, we've assembled a really phenomenal team of forensic engineers, academic researchers, and federal investigators with expertise across many disciplines to lead the 6 projects that I've listed here. So these projects include a building and code history project, an evidence preservation project, remote sensing and visualization project, a materials characterization project, and a geotechnical and structural engineering projects. So now I'm going to very, very briefly introduce you to our 2 other statutory national programs that are housed at NIST. Those are NEHRP and NWERP. NIST is the lead agency for both of these programs. So let's start with NEHRP. I'm an earthquake engineer, so this is originally my home, my professional home. So NEHRP, or the National Earthquake Hazard Reduction Program, is our oldest statutory program. It was signed into law in 1977 in response to the San Fernando earthquake. And for those of you that are not earthquake engineers, the San Fernando earthquake was the dawn of modern era for earthquake engineering in the US. It galvanized the country to improve the performance of the built environment in response to seismic events. NIST is the lead agency of this program, and it also includes FEMA, USGS, and NSF. And the 4 agencies work together to develop, disseminate, and promote knowledge, tools, and practices for earthquake risk reduction and improve our nation's seismic resilience. So this is a very brief overview of the strategic plan for NEHRP. It's organized into 4 strategic goals, which collectively represent the strategy to support the program's mission. The goals range from research, very basic research done by academicians, all the way to its practical side, so disseminating and implementing tools and practices and policies that help enhance strategies to withstand and recover from seismic events. I want to focus very specifically on Goal D. So Goal D encompasses our ability to learn from post-earthquake investigations. And it's really important for me to say this because at NIST, we have multiple authorities that we can use to deploy to natural disasters and either study or investigate them. So I mentioned this National Construction Safety Team Act is the first one, and NEHRP is another example of an authority that we can use to deploy in the US and around the world. So I want to switch gears real quickly to NWERP. NWERP is our National Windstorm Impact Reduction Program. And I'd like to say that tornadoes, thunderstorms, hurricanes, and associated flooding with any of those types of events are the deadliest and most costly disasters in the US. Every single state, every single one of them in this country is exposed to some form of windstorm hazards. The National Windstorm Impact Reduction Program is our youngest of the 3 statutory programs. It was established in 2004 and is potentially going to get reauthorized soon, we believe. And so really the objective of NWERP is to translate the fundamental understanding of wind behavior into the reduction of windstorm impact. NIST, again, is the lead agency of this program, and it also includes FEMA, NSF, and NOAA. And like NEHRP, it also has a strategic plan that's organized under 3 strategic goals in this case. And now these goals collectively represent the strategy that support its mission. So NWERP is yet another authority that we can use at NIST to deploy to disasters, and we're currently using it in Puerto Rico to conduct a research study. So I mentioned before that we're doing this investigative work in Puerto Rico to understand the performance of critical buildings, but we're also doing a research study under NWERP to understand the long-term recovery process for our manufacturers, businesses, healthcare sector, the education sector, and key distributed lifelines. So NIST has a range of authorities that I've mentioned, NCST, NEHRP, NWERP, all of these we could use to respond to disasters and failures that occur in the US, but we cannot possibly to deploy to every single one of these, nor launch a full technical investigation to look at all of their impacts. So therefore, it's really challenging, but we have to ask ourselves, which events should we go to? And so our advisory committee years ago had asked us to be very standardized in the way that we make decisions about responding to events. And so this flowchart demonstrates that decision-making process. It includes a quantitative piece and a qualitative piece. We use these scores to recommend possible field deployments. Then if we do deploy to an event in a preliminary sense, we use that opportunity to collect primary data. And that allows us to either update or confirm any of our scoring sheets that we did ahead of time before deployment, and then possibly subsequently recommend to our NIST director that we ought to do a full NCST technical investigation. An alternative to an NCST investigation is to conduct either a focus study or another research project under another authority, which we've done recently in response to wildland-urban interface fires in California. So now this leads me to the connection with IDS. So regardless of the avenue that we choose at NIST, all of the activities that I've just described that are related to making a decision to either deploy or subsequently investigate impacts of an event involve a lot of data and very different types of data. And a few years ago, I was seeking to better standardize our field measurement tools and methods, and especially to improve our data tools to support our science and also to enable collaborations across the federal government. I stumbled into Alex's office one afternoon, I hope you remember that, Alex, and I explained to him the data challenges we were having in our disaster science community. And then he described to me his own journey, including his development of SciServer, and then IDS. And although my focus is on earthquakes, storms, and structural failures, it appears very different than astrophysics, the fundamental hurdles that I am encountering and have encountered for years are very similar to Alex's journey. And so began this very fruitful collaboration with the Hopkins NIST prep program that includes Alex, Gerard, and Arik. And so we've been working for the last couple of years to adopt a data semantic standards for our disaster programs, foster interoperability between NIST data repositories and other data repositories, design a public database, and also combine traditional data management and access services with computing resources. So truly, SciServer was a wonderful accident to encounter. So this Hopkins collaboration leverages services that are provided by SciServers, and this is storing, accessing large disaster data, also server-side analysis using Jupyter Notebooks, which has been incredibly helpful. And we use all of this to inform critical disaster response activities. This enables us to have collaborations with our outside stakeholders, and that includes other government agencies. So we typically have very limited time to decide on the most appropriate response during an event. And that includes the decision process, followed by the focus of a potential preliminary reconnaissance, and then followed by scoping a subsequent investigation or study. So in order to improve our processes at NIST, I really wanted to standardize and streamline data collection methods. And this really could not have been a better partnership to do that with. And so what you're seeing here is what we call the SciServer flywheel. And it's this idea that we have to pull in information from all of these government agencies, from private sectors, from academia, internalize it, make decisions ourselves, scope out our projects, and then produce results and data that others can then use to improve their science. So thanks to IDS scientists, we've deployed SciServer on Amazon Web Services at NIST. We require registration and secure login using NIST credentials. We've been approved to use SciServer at NIST for low impact data. And right now we're running security scans to expand its use to medium and high impact data. We've also taken steps to implement this flywheel that I just showed to automate our manual disaster scoring and decision-making process. So even though we have checks in place to minimize biases that are introduced by subject matter experts when they're scoring events, their process and our decision-making are absolutely improved when critical and quickly changing data about hazards, damage, or social risk are automatically pulled in for analysis. So as an example, we've developed a workflow that mimics the manual steps that would be required to calculate the event consequence of a storm in our decision-making process. So the total weighted score considers mortality, exposed population, hazards or other failure intensity, and physical damage. So you can see the actual physical score sheet on the left-hand side, and the yellow boxes are the scores that subject matter experts gave for that specific storm, which is Hurricane Michael in this case. Now the algorithm, which you see on the right, or the workflow you see on the right-hand side, is implemented on SciServer, and it pulls data from authoritative sources such as the National Hurricane Center and Census, and it's used to predict the same event consequence score that we would have done manually and have done manually for years during an approaching storm. Now we can compare these manual scores on the left-hand side to the SciServer output on the right-hand side. And so I'm just going to go through some of these to give you an example on how we're using this to automate our scoring mechanisms at NIST. So the algorithm that we're implementing automatically pulls data from the National Hurricane Center's feeds. Now, this is fantastic, and we use these feeds to predict storm severity and coastal inundation as shown in the highlighted workflow. So we don't have to wait to receive information from one of our stakeholders in another federal agency. We can automatically start pulling in the information as the storm is developing. And why is this useful? So we need to predict a landfall point and roughly an associated time for that, so that we know the potential wind speed and gusts that are going to be experienced by a community. So we use the advisory forecast track, we use the cone of uncertainty, and we use watches and warnings, all published by the National Hurricane Center. And this gives us predictions for these values at points representing the center of the storm up to 5 days from the present location. Now, the computation comes from a linear interpolation on a fine grid between these points for each of the target variables. And we intersect the geographical location with continents so that we can take the point closest in time as a landfall point. Now, this is very important because we want to predict where the storm is going to make landfall, so we can start predicting what kind of impacts it's going to make and whether or not, based on those impacts, we might make a decision to deploy a team to the field. So in addition to the wind hazard part of a storm, there's also the water hazard part of the storm. So for coastal inundation, this plot shows predicted probability of storm surge exceeding 1, 3, and 10 feet respectively for a region that's 20 kilometers extension into the sea off the coast. The brighter colors represent higher probability of storm surge. We don't do any calculations here. We draw these numbers directly from the National Hurricane Center, but we use them to score in our rubric the probability of having maximum surge of 1, 3, or 10 feet. And this becomes very important in our decision-making process to look at impacts in coastal communities. And so that takes care of the left branch of that workflow. Now, the center branch of this workflow is really focused on using these storm tracks that I just mentioned and the wind field predictions to estimate exposed population to such an event. And we combine feeds from Census and the National Hurricane Center to predict this exposure along the storm's trajectory. So in addition to that, the live data feeds that we're getting from the National Hurricane Center, we downloaded shapefiles from Census Tiger API for state, county, and census tract polygons. So these are all reformatted for efficient loading onto SciServer, and they're stored in a database which allows for efficient querying with spatial constraints. So the predicted wind swaths are derived from the forecast wind radii. They're interpolated by building convex halls around them, and then we create a union of that. So that exposed population is calculated by summing the population data in the census tracts that overlap with that predicted swath for the hurricane strength winds. Now, this becomes really important because we want to understand the possibility of exposing individuals to strong wind fields that may need investigating from one of our authorities. And then finally, we would like to automatically grab data fields for disaster-associated injuries and mortality, but these are really not readily available yet, unfortunately. So we've been working with the CDC's Social Vulnerability Index, truly only as a placeholder for estimating mortality until we have a better way to automate this process. And so we use that same downloaded data, census data that I mentioned before, to estimate social vulnerability by using CDC's SVI, Social Vulnerability Index, along that same predicted swath for the hurricane strength winds. And we hope that some of the recommendations that are resulting from our Hurricane Maria investigation on the mortality project specifically help standardize death certificates, the training on populating death certificates, and then the subsequent reporting of mortality and morbidity after disasters. So together, social vulnerability, morbidity, and mortality are all important factors when considering disaster impacts, and all should be considered when we make decisions about deployment. So the SciServer collaboration with our disaster statutory programs, and I've introduced 3 of them today, has shown me that it's really difficult to aggregate large geographically distributed data sets and do any kind of analysis without them being co-located. So we're trying to avoid the mistake that Alex mentioned just a moment ago of creating the mother of all databases, and instead recognizing that building ontologies and data models are hard. It's something that we're facing and moving forward to try to improve on. So we do realize that these real life uses require interactive exploration before approaching big analysis. And we're enthusiastic that we're taking the necessary steps to improve how disaster data is used across the federal government. So at NIST, we're really motivated to publicly release as much data as we can from any of our disaster statutory programs. And we've taken the steps to publish some of our data and our field instruments. So these are survey instruments on platforms that are frequented by academics and researchers like DesignSafe shown here. We're also using SciServer as an example to communicate back to our federal partners on why their data feeds are necessary for emergency response and how new data sources could be really helpful for our collective efforts in responding to events. So this is just, I've shown just an example of how we're using SciServer at NIST for the decision-making part of it, right? And so at that point, we're just collecting as much information on any approaching storm or an event like an earthquake that has already happened, or like the building collapse that happened in Florida. And when we're done making a decision about the next steps that NIST is going to do to study those events, we then get into really interesting science. And I just wanted to show you some examples of the kinds of products that we have already from our Hurricane Maria investigation and expect to have from our Surfside investigation as well. So we are truly hopeful that we can continue to grow this NIST SciServer collaboration to combine traditional data management and access services with computing resources so that we can advance our own science at NIST and also produce better data for the community. So I wanted to conclude by really sharing my appreciation for overseeing all of these disaster programs at NIST. I really sincerely believe that advances that we're making under these national programs are going to force important changes in building code standards and practice. It was a really difficult decision to leave your lovely community and move to the federal government, but it's this kind of impact that motivates me every day. And so I would be remiss if I did not also include in my talk a few links for all of you to follow up on. If you want to learn more about any of the statutory programs that I mentioned today, that includes our National Earthquake Program, our National Windstorm Program, the National Construction Safety Team Act. Also, if you're curious about any of our active investigations, there's a link to our Champlain Tower South investigation, as well as our Hurricane Maria investigation. Both of these websites actually update very regularly, so you really can track the activities that are undergoing under both of these investigations. And I didn't get an opportunity to get into the community resilience work at NIST, but it's one that's dear to my heart, and so I wanted to share the link with all of you today as well, so you can learn more about it. And finally, opportunities at NIST. We have many. We have a SURF program, so Summer Undergraduate Research Fellowship Program. We also have a NIST Pathways program that enrolls students from high school to post-grad. We have an NRC postdoc fellowship that is very special. We attract really high qualified postdocs to NIST using this program. So if you have any graduating students that might be interested in the kind of work we do at NIST, I urge you to send them this link. And then finally, our prep program, which I mentioned today. So this really is, I mean, it's a professional research experience program, and it's fantastic because it allows NIST to extend its capacity scientifically and engage with our partners on the academic side. And so I'm really pleased that Hopkins, as well as 4 other universities in the local area, are part of this prep family, and that we can lean on you all for very specific needs and capacity building when projects require it. And then finally, we have opportunities for sabbaticals, guest researchers, and many others. And if you have any questions on any of that, please don't hesitate to reach out. Some of these programs are US citizens only, and I tried to designate those, but not all of them are. And so I really encourage you to encourage your students to look at NIST for future opportunities. And I am just a few minutes shy of the end of my time and wanted to leave some time for questions, but I wanted to just share my sincere gratitude for inviting me to your symposium. And I've really enjoyed collaborating with IDIES scientists for the last couple of years, and look forward to more collaborations. Thank you.
Yeah, thank you very much, Judith, for the wonderful talk. And I would like to ask the audience for questions. Please submit the questions to the Q&A or the chat, please. And then I will read it aloud for everyone. So in the meantime, can I ask one? So in summary, have we actually accomplished with the SciServer the goals you actually set out, or you were hoping for? Or what would you like to see us do better or more?
I mean, I think we have, but I also think we've encountered challenges, right? So being able to implement, starting out with that, we needed to have SciServer inside of our firewall. So that was like the first challenge. So that wasn't something that we were expecting to need to do, but then that was no problem. We found ways to do that. And so we have our own NIST SciServer, which we love to call that. And that has been excellent. And so I think the next barrier for us is that we really have only been working with this like low impact data, but a lot of our projects involve medium and high impact data. And so we want to be able to use the computational side of SciServer fully, right? And we can't do that unless we have approvals to use the platform in this way. So I would say that's our next big challenge, is doing that. I think a third challenge might be buy-in, right, from engineers and scientists who feel like they have to learn something new. And so really having your team integrated into our projects, having them attend, our investigative meetings, for example, and they're part of the team, I think is helping. But I still think we have a ways to go.
So we have a question also from Gerard. How might other groups from JHU participate in the PrEP program?
Oh, sure. So I do think that anytime that there are prep opportunities and NIST scientists will post like an announcement, right, of a new upcoming prep opportunity. That's one way, and that's a passive way, never a direction that I like. So a more active way is that I would encourage you all to reach out to colleagues at NIST, people that you've worked with, people you would like to work with, and just remind them that this program exists and what the purpose of the program is. It's really to add capacity to NIST, right? So ideally, I would love to have a ton of computer scientists to come work for me. That's just not practical. And so it's likely not going to happen, but this allows me to tap into a tremendous resource and add capacity to our national programs without internally building this capacity.
Now I have one last quick question. So when we first chatted, you also mentioned that you see a possibility of serving FOIA requests out of the SciServer.
Absolutely.
So what needs to happen to be able to do that?
So what needs to happen is we need to get approvals to complete our, so ideally our workflow would end in publishing data, right? And we have, as part of, kind of our plans for this coming fiscal year, to develop a workflow that uses our NIST approvals process to get from, scientific data in a project to being published and then made available to the outside world. And if we can do that, the ability for us to be, and we wouldn't have to be responsive to FOIA requests, we could just put everything out publicly and not have to deal with FOIA requests at all, right? That would be the ideal situation, is just make it all easily available, make it all discoverable, and I really think that should be the ultimate goal, even if we didn't have kind of this extra effort of addressing FOIA requests.
Once again, thank you very much for
There's actually one more question in the chat, if there is time.
Okay. Sure.
So now, can I read it out?
Yes, please.
So Nadia is asking, is it difficult to deal with the constantly changing types and nature of data from so many different sources?
Absolutely. Every single disaster is unique. Every single disaster brings with it unique data sources and things that we need to look at. But what we're trying to do is, for those things that are not changing, standardize those, right? So this idea that we're manually scoring events is, to me, is just unnecessary, right? I believe that you need the subject matter expertise as added input, right? And value added, but being able to just have ready for you all of these resources that are being populated by other agencies and outside, private sector partners, I think is really critical and something that we really need to automate and continue working on. It also helps us give feedback back to our federal partners and say, look, this is great. This is how I'm using this data feed and that data feed. But wouldn't it be nice if you also populated your data feeds with like damage predictions? Because I would love that, right? And so there's all these, it really allows us to have better conversations when I have visual tools to explain to them the importance of openly sharing and quickly sharing this information, or setting up APIs, right?
Yeah. So once again, thank you very much for the wonderful talk, and it was nice to have you back here and talk.
Nice to be back.
Yeah.
Thank you very much.
Thank
for a
you,
wonderful
Judith.
symposium.
So our next talk is a seed funding project update from physics and astronomy professor Nadia Zakamska. Nadia, whose research on the role of supermassive black holes in galaxy formation has garnered her several prestigious prizes. Today, she is going to talk about using upcoming new data on white dwarfs from the Sloan Digital Sky Survey, which incidentally was one of the projects that led to the founding of IDEIES, and other surveys to learn more about the origin of type 1a supernovae. So Nadia, you have 20 minutes, and I will probably give you a raised hand or something at 15 minutes.
You hear me okay?
Yes.
Okay, excellent. So thank you so much for being here. I'm a professor in physics and astronomy. This is a project that I am doing in collaboration with a couple of brilliant students, Shanti Huang in physics and astronomy, and Vedant Chandra, who was both in physics and astronomy and in applied math. And we're also collaborating with a professor of applied math and statistics, Tomasz Budovari. We have an IDIES seed grant to search for elusive progenitors of type 1a supernovae. So I'm going to give a quick update on the status of this today. This is we're on a completely different scales from the previous talk. I'm gonna zoom all the way out first to the scales of the entire universe, and then a little bit closer in on the structure of our own galaxy. Type 1a supernovae is a major puzzle in astrophysics. So supernovae in general, just the word means stellar explosions. They are very, very bright. They're visible out to very large distances. But type 1a supernovae, so they come in different types. You can classify them using a variety of methods. And so one of those types is these type 1a supernovae. And they're very special in astrophysics. Because if you measure their light curves very, very accurately, so their brightness is a function of time, then it turns out from the shape of this light curve, you can guess the intrinsic brightness of the source, and therefore from the intrinsic brightness of the source and the apparent brightness of the source, you can know the distance to the source. And distances in astronomy are very, very difficult, but type 1a supernovae essentially started what we now understand was a major revolution in our field in the last 20 years that enabled so-called precision cosmology measurements, meaning that we now can measure the geometry of the universe to precision of about a few percent. So among various other things, type 1As were used in the discovery of the accelerated expansion of the universe, and the Nobel Prize in Physics in 2011 was awarded to 3 scientists for this discovery, including to our colleague in physics and astronomy, Adam Rees. So here in this figure, I'm showing a distant galaxy, well, not so distant, a relatively nearby galaxy with the star that wasn't there in the previous exposures, and then boom, at some point, the star appears and then slowly fades over time. So this is a type 1a supernova explosion in this particular galaxy. One major puzzle in astrophysics, though, is what gives rise to these particular explosions. And this is a decades-old puzzle, and the community has gone back and forth on this question. But right now, based on totality of all observational evidence, it seems that the progenitors of type 1As are binaries of white dwarfs. So one sentence of white dwarfs. White dwarfs are the end products of stellar evolution of relatively normal stars like our sun. So several billion years down the line, the sun will be a white dwarf. But so now I'm talking about 2 white dwarfs that are very, very close together, that are orbiting around their common center of mass, that produce gravitational waves, and then eventually their orbits shrink, and then they merge, and then if their combined mass is high enough, they explode as a type 1a supernova. Okay, this is what the community sort of is leaning towards in terms of what the progenitors are. But if that's what they are, then we should have them in our own galaxy, kind of on the way to that explosion. So where are these binaries? And this is a big, long-standing problem. So in principle, discovering stellar binaries and characterizing them is not, the idea is not very complicated. So stars very commonly have features in their atmospheres, like an absorption line with a known laboratory wavelength. And so when there are 2 stars orbiting the common center of mass, and there's some feature at some fixed wavelength, if this star is moving away from us, then it's Doppler shifted away from us due to the motion of the star. It appears redshifted. And then if this star is moving towards us, the feature appears blue shifted. And so as the orbit continues, as the stars move on their orbit, these 2 absorption features move around. So So this is a classical signature of binary stars, very well understood and observed by the community. With white dwarfs, we are facing a very unique challenge. White dwarfs are very compact stars. They have very high surface gravity. Their absorption lines are extremely broad. And therefore, instead of the two well-separated lines, like in the previous case, you get this kind of blobby something. So fine, maybe you can sort of still see the difference in shape between these three cases. And so now I'm adding just a little bit of noise to this situation. And now I really cannot possibly tell you that there's a binary here. So this is the challenge. White dwarfs are very compact stars, so they are very faint. So those are noisy spectra we're talking about analyzing for this problem. So why do I think that the situation is suddenly different, and why did we propose for this project now? And the reason is the beginning of the Sloan Digital 5 survey just a few months ago in November 2020. So Hopkins in general and IDIES in particular played a fundamental role in the development of the Sloan Digital Sky Survey. Sloan survey is now over 20 years old, but every several years they change their science program. And so what is completely unique right now is that they have just started the Sloan 5 program, which will focus specifically on galactic stars. And so we will have this unprecedented set of spectra of 4 to 6 million stars, including 200,000 white dwarfs. And just to give you an idea, of the sort of the increase in the database size, so to speak, the total number of all white dwarf spectra obtained by everybody ever before is sort of in the 20-30,000 ballpark, meaning that Sloan 5 is going to increase the number of available spectra of white dwarfs by an order of magnitude. So to me, this is a big deal. To me, this seems like, okay, now is a really good time to develop tools to identify white dwarf binaries. So my students and I are leading this project in the Sloan Digital 5 survey. We're part of the white dwarf working group. And so the way I think about it, there are sort of 4 data challenges to this problem. First, we need to identify white dwarfs in the catalog, and also white dwarfs come in slightly different flavors. So we need to classify them. The second step is we need to be able to make physical measurements from the spectra, so masses, radii, temperatures, to actually measure stuff. The third step is to identify these very interesting candidate binary white dwarfs. And then finally, ideally, based on this amazing new data, we will be able to understand whether the statistics of binary white dwarfs in the galaxy near the sun are consistent with the cosmic rate of type 1a supernovae. I'm not going to say a huge amount about classification. I'll just mention briefly that there are some standard ways of doing this, like template matching, and there's some interesting new ways of doing this using various machine learning techniques. So we're exploring all of those things. But so there are things that we can do very well and very easily that are based on the global shape of the spectrum or big features in the spectrum. But I'm sure you won't be surprised to learn that the most interesting things that are of interest to us specifically for identifying candidate binaries are also the most difficult. So there are some very, very complicated, very subtle signatures that we need to be able to distinguish binary white dwarfs from weakly magnetized white dwarfs and whatnot. So, so that's where the difficulty is right now. It's very amusing that right now the classification of white dwarfs in Sloan 5 is done by the so-called human neural networks. And what this means is a dozen scientists once in a while sit down and stare at a few tens of thousands of spectra to classify them by eye, which is okay. The survey is still kind of in its childhood diseases stage. We need to iron out a lot of data issues. So having all these eyes on all these data are very important at this stage, but of course we cannot sustain that with for 4 to 6 million spectra. So at some point we need to transition to much more advanced ways of doing this. But right now we're sort of developing the training set, so to speak, for all these future efforts. So never mind classification, there's a way to identify some robust white dwarf spectra now, a few thousand of them relatively straightforwardly. So this is an example of a white dwarf spectrum with hydrogen atmosphere. And I've already said that the difficulty with white dwarfs is that these absorption lines are very, very broad. And so in terms of velocities, they are broader than the signal that we're looking for. So what we need in order to measure the signal we're looking for is we need exquisite modeling of the absorption lines themselves. So we started working on this problem a couple of years ago, and we discovered that so there exists some models for these features, very, very complicated, physically motivated models, but they're proprietary. And they're proprietary to a couple of groups who are doing the development of these models. And that is not the standard in our field. For normal stars, there's plenty of publicly available templates and models. So it was a little off-putting because we were a new group. We wanted to play with spectra, and all of a sudden we discover we can't measure anything because the models to get any physics out of our spectra are not publicly available. So we went around this and we published this paper called Computational Tools for the Spectroscopic Analysis of White Dwarfs. So what we did is one of those groups made available a very coarse grid of their models over the kind of relevant parameter space, which is the temperatures and the gravities of these stars. So they did not publish their code that computes the models, but they published a very coarse grid of models. And what we have done is we interpolated over this coarse grid using artificial neural networks. And so now for any surface parameter of a white dwarf, we can generate a model spectrum, and then we fit the data just like we normally do. And so the interesting result is that our fitting procedure is not any worse than the one that is based on the actual physics. So I'm showing here the results of this fitting. This is by one of the groups with proprietary access to the codes. This is a white dwarf with absorption. So these are different absorption lines, and the data and the models, as you can see, line up very, very nicely, and they get the parameters of the white dwarf. So this is our tool that is publicly available at this link that anybody can now use. Our methods don't know anything about the underlying physics. They get these publicly available coarse models, interpolate amongst them in a clever way, and fit the data. And actually, our fitting procedure is doing this fit in a fraction of the time that this procedure is doing this. We have extensively tested this, and the answer is that our final parameters that we derive for our white dwarfs are not limited in terms of their accuracy by our interpolation procedure. They're only limited by the quality of the underlying models. So if somebody gives us better models, we will do a better job. So now we can, measure things, and we have made this tool publicly available. So now let's go to the next step of identifying candidate binaries. So I'm showing you again a spectrum of a hydrogen atmosphere white dwarf, and I want to zoom in on these two absorption features. And so Sloan, because Sloan needs to acquire spectra of a particular signal to noise, they have to stare at these faint sources for a very long time. So to collect enough photons to get to the necessary signal to noise. So they actually do this in batches of 15 minutes. So they take a 15-minute exposure, 15-minute exposure, etc. And so in principle, for most applications, what you want to do is you want to combine these 15-minute exposures. But for our application, we don't, because if we treat them separately, then we can measure some time variability between them. So that's what's shown here. This is a sequence of 4 15-minute exposures. And maybe you can see some, it's all noisy. And maybe you can see some split lines here. Well, that would be the key signature of this kind of orbital motion that I showed you before. So is this real? Is this not real? How do we find out? So this is a happy example because this object turned out to be real. We published this just a month or two ago as
5 minutes.
Yeah. Okay. We published this just a month or two ago. This is a 99-minute double-blind white dwarf binary from SDSS-5. This is actually the very first science paper of the Sloan 5 survey. We obtained better data from Gemini telescope, which is a larger telescope, so you can do shorter exposures. And this is what's shown here. This is a bit of a complex visualization, but if you take a horizontal line here, this is one spectral exposure. And if you see yellow, this is where the absorption lines are. So in, for example, this horizontal slice, there are two absorption lines, 1 and 2, one from each star. And then the characteristic kind of S shape is due to the orbital motion. So when you see two S shapes, that means two stars going around their common center of mass. So this is a real discovery made with fresh new data from Sloan. And the hope is that we are going to be developing tools, or we are developing tools to kind of discover many more of these objects. This particular one is not yet a type 1a progenitor. It's not quite massive enough, but we are looking for objects to populate this more massive part of this diagram. And as I said before, Sloan has promised to increase the number of white dwarfs by an order of magnitude. So we're very hopeful. And finally, this object is short enough period and close enough that it's going to be a pretty strong source of gravitational waves for the next generation of gravitational wave experiments. So let me conclude. Type 1a supernovae are extremely important in modern astrophysics, yet we still don't know what their progenitors are. So in this program, we want to discover white dwarf binaries, which may be the progenitors of type 1a supernovae. Right now, we are in step 3. We have a dozen strong candidates that we are following up with various big telescopes, Gemini, Magellan. And we are currently developing analysis tools for this emerging new survey. And of course, we're dealing with a lot of data challenges as we're doing this. But I hope that the end result is a few years down the line, we will be able to tell whether there are enough white dwarf binaries in our Milky Way galaxy to explain type 1a supernovae. Thank you.
Thank you very much, Nadia. Let's see if there are any questions. So in the meantime, I had 2 quick questions, actually. Do you think that for the classification, you might be able to benefit from some kind of crowdsourcing, like a Galaxy Zoo type thing?
This is, I mean, what we are doing right now with our human neural networks is basically crowdsourcing. What is really challenging about this is the same reason that it's very challenging to automate this for now, because we can do the crude classifications using a whole bunch of different techniques, and that does not require crowdsourcing. But the interesting features, the scientifically interesting features, are extremely subtle. And so we are developing this both kind of by eye and quantitatively in parallel. So, you know, we are informing our quantitative approaches to it by our by eye classifications. And the learning curve, unfortunately, for this classification is very steep. So you kind of have to have a lot of experience of looking at these spectra to know what to look for.
And my second question was, how exactly are these proprietary models, or rather the proprietary aspect, enforced? Like, would you get into some legal trouble if you use them, or do they have a patent?
We are very nice and warm and fuzzy. So we're making friends with all of those people. So there was a little bit of politics involved. And when we first reached out to one of those groups, they were not super enthusiastic about us doing this. They were very concerned that being blind kind of to underlying physics will lead us to make mistakes. But then when we actually produced this result, I think they were pleasantly surprised by how well this worked. And so we're actually collaborating with them now to increase the size of the grid. And, there continues to be a little bit of politics involved in this. But in general, the hope is that this is going to be a problem that's going to be solved both by them kind of being more open to releasing more of their results and by us improving our techniques of generating these model grids for the public consumption.
Okay, thanks. Let's hope so. And thanks again for a wonderful talk. So next up is an introduction and update on SciServer, the generic science platform for collaborative data-intensive science that was developed right here at IDEAS. The talk is by Dr. Gerard Lemson. I hope I pronounced that right. Who is the IDEAS Director of Science, as well as the project manager for SciServer. So Gerard, I'll give you a 8-minute, raise my hand or something at 8 minutes. So you'll have 2 more minutes at that point. Thanks. You're muted.
Sorry. As in each IDEAS Symposium, I'll give a short overview of what happened in SciServer in the last year. SciServer is no longer formally funded in its own NSF, from its own NSF grant, but we've been working with other people. So it's a short history. So SciServer is basically an implementation of this observation by Jim Gray that this 4th paradigm of science is that science is these days done with large amounts of data, where people try to apply machine learning and other statistical techniques to actually make sense of this data. And it's also done in large collaborations. And so this causes some problems for typical scientists. So if the data is growing very large, you may need special expertise to actually be able to deal with that. For example, the way SDSS started dealing with using relational database technology to deal with their catalogs. At the same time, people are actually interested in the data, so it is important to make it public and to share it with others. And again, that requires techniques more like of web design, etc. The data are generally heterogeneous, so it becomes hard to actually combine them together. You may need to actually start scripting. It's not that it's all kind of point and click anymore. And as I said, it's increasingly collaborative. So you actually want to be able to work for a while in groups and collaborations with your data. So SciServer implements or supports all of these features. This is the SciServer web application, and people can go and register. See the link. So we basically, while designing SciServer, and what we recognize for different collaborations that we have is there's a couple of typical usage scenarios. Now there is the dissemination of big data. On the right in bold are a couple of the projects that we're supporting. Some of them I will discuss a little bit more detail later. We support relational database platforms. We allow people to write code close to the data and run it on our compute infrastructure here at Johns Hopkins. We have a strong support for sharing of resources and for making certain parts of resources still hidden from all the users. We support data aggregation and integration easily. We have now also a bunch of external SciServer instances. The one at Johns Hopkins is no longer the only one. Some of our developers have been collaborating and have been assisting other groups with in quite sophisticated UI development. And we also support certain educational efforts. So Alex had a small diagram. This is the latest updated version. So all of these colorful boxes are basically projects that we have supported and that we still support. Recently I started actually coloring the orange ones that actually provide some funding for us as well. So the sustainability of SciServer at the moment is coming from collaborating in projects, MOUs, participating in grants, etc. So this past year, we've had some personnel changes. Sahil, who was our main UI developer, the main one responsible for our main dashboard, he left. He went back to follow up with the masters. Steve Handy started work with us from the Technology Innovation Center that has an own version of SciServer, and he works 50% with us to try to bring out to our source code together. And we've recently hired 2 new people who are not directly their IDEAS personnel. They're not going to be directly working on SciServer, but on the longer term, probably they will be here as well. We've done some work on the SciServer platform. The dashboard is configurable, which is useful for the external deployments. Steve and Manu started working on SciQuery, which is going to be a replacement for our database web application. For certain technical reasons, we wanted to do that. Then we wanted to generalize away from having only SQL Server support, but only other database systems. New compute images are continuously being created. Courseware to make it easy to set up an environment inside of SciServer to run a class. This needs still some UI work, so to follow the person who we've offered a position to follow up, Sahil, will do work on that. And there's some other features. One is also that monitoring. We started realizing that there's probably one crypto miner who keeps coming back, and we need to monitor to be able to catch them. There are some related projects, as I mentioned before. There's the new Turbulence database project will be more SciServer based even than it was before. And then there's these nice other tools. So another main change in this last year is that we've actually moved. Most people who used to be on the 3rd floor in the Bloomberg building, this separate wing, the IDEAS wing, all of us are now up on the 6th floor. Except, of course, there's only a few people at the moment who generally come there. So I'll just go over a few recent projects. Luckily, Judy already mentioned a lot about one of the projects, so I can skip that. So there's a new prep project that started early last year, or early this year, end of last year, with PI at NIST, Lyle Levine. So what people are doing there is they are creating that. This is AM Bench. It stands for additive manufacturing benchmarking, and additive manufacturing is a kind of sophisticated 3D printing. And so what they want to do is they want to understand, since it's additive manufacturing, it's becoming more and more popular also in industry. What people want to know is whether they understand the properties of the objects that are coming out of this. And so at NIST and some other laboratories, they're creating some of these 3D print objects, as it were, like the one in the top left. And they do all kinds of measurement on them, like X-ray diffraction and all kinds of other stuff. The data sets that are coming out there, they want to publish. And the goal of that is that people who do models of 3D printing, they can actually compare their models to what comes out of the data. The goal is to have SciServer host this data and allow people indeed to do the analysis close to the data. Another thing is a Seymour project that Johan from our group works with, Frederick Tan and other people. This is used in education at the Clovis Community College in California. They're using SciServer with some specific setup, a specific compute image, specific data sets to use it there in the classroom. And recently also the annual practical genomics workshop also used SciServer. As I mentioned, Alex already mentioned Astropath. We'll hear more about that later in this symposium. This is a wonderful viewer.
2 minutes.
Used online. Yes, thank you. A similar viewer with both was also built in this case with Dimitri, and Sahil visualizes ocean circulation and other features of ocean circulation models from the Poseidon project. We started doing some proof of concept work with Alana Vertic in our laboratory to make tools available that their single cell consortium is interested in. So we have an image so that in your Jupyter Lab container that you can start in SciServer, you can run cell by gene. And we made some extensions to our infrastructure to give their project basically the right to create storage volumes available for their sub-projects who want to keep their data still somewhat more isolated. And these are 4 different external deployments of SciServer. The top left is the precision medicine analytics platform. Cruncher is a version of SciServer. This is the one that we're trying to start bringing together with our current code base. The top right is the National Astronomical Observatory in Japan. They have a version of SciServer, but it's somewhat limited. They have their own tools, but they use the sharing features and the compute features. The bottom left is the Max Planck Institute for Extraterrestrial Physics that uses an on-premise installation of SciServer for the eROSITA and HEDEC surveys, and the bottom right is the one at NIST that Judy already told about. So please try SciServer. If you would like to work with us and have some of your data sets either be public or at least shareable by some of your colleagues all over the world, please contact me about that. And I want to thank the SciServer, the members of the IDIES and the SciServer teams. Thank you.
Thank you very much, Gerard. I was actually going to, if there are no other questions, I was going to ask what is the quickest way for a data provider to kind of get what, and I think basically contact you is the answer.
That's correct.
Okay. I don't think there are any more questions. So let's just move on to the next talk. So our last final talk in this session is another seed funding update from Dr. Jonathan Ling, who is an assistant professor of pathology in the School of Medicine. His research combines bioinformatics and genetic engineering to develop innovative therapeutic strategies for age-related neurodegenerative diseases. He will talk about using public sequencing archives to uncover how ALS develops. And I'll give you, I guess, a 15-minute heads up, and that will leave 5 total minutes. So if you want to leave some time for questions. Thanks.
Great. Thank you very much for the introduction. Okay, so today I'll be talking about an effort that has been ongoing to leverage public RNA-seq data sets for better understanding neurodegenerative diseases such as ALS. ALS is a terrible disease. It has an average life expectancy of only 2 to 5 years. Ice Bucket Challenge has brought it to the public view, but many people have been dealing with this disease for years, and there's a dire need for a better understanding of how this disease progresses, and hopefully which would lead to treatments and therapies. What many people don't know is that ALS is actually now recognized as a spectrum of diseases that shares commonalities with another disease called frontotemporal dementia. And while the areas of the brain that are affected are different, the genetics and pathology are intertwined. For example, some family members that carry a causative mutation called C9 or F72, siblings can have both pure FTD or pure ALS, which is quite surprising. And really what our lab has focused on is this protein called TDP43, which is present pathologically within 97% of ALS cases and 50% of FTD cases. So in 2015, we identified a function of TDP43 that we believe is causative for neurodegeneration, at least to some degree. In the pathological sections that we see, there's TDP43 that mislocalizes and aggregates outside the nucleus, and where its primary function, we believe, is to repress these events called cryptic exons. So in the conversion of DNA to RNA to protein, only certain regions of the DNA are spliced together, and these regions are called exons. TDP43 normally sits in between these exons to prevent novel neoexons from occurring. And when you have the appropriate splicing, you get a normal protein. However, as we saw, as you can see here, normally TDP43 is in the nucleus. When it leaves the nucleus, we find that these cryptic exons get incorporated aberrantly and cause defective proteins, and it's bad for the cell. So we have worked to identify and characterize a lot of these cryptic splicing events by using junctions. And this is information that can be gleaned from sequencing data. Essentially, we have the ability to measure sequences that are present within a cell. And sometimes these sequences jump, when we align them back to the genome, they jump across two disparate regions in the genome. And that process can only occur due to splicing. So you would imagine within an RNA-seq data set that has TDP43 knockdown, you would see this junction present, but you would never see this junction in control. So these are very unique sites or sequences that can be pulled out of public data. And our work has now identified that cryptic exons in TDP43 mislocalization occurs in a variety of other diseases, such as Alzheimer's disease and a muscle wasting disease called inclusion body myositis. So you can see the presence of cryptic exons in disease. Now, we've worked with Ben Langmead in computer science, as well as Christopher Wilkes, in a very collaborative and exciting project that led to the development of ASCOT. This is a database where we try to leverage a IDEA-supported effort to summarize all publicly available sequencing data. And these two papers, and we're continuing to update these databases, are publicly available summaries of all these sequencing data sets that are online and deposited by other researchers across the world. Snaptron in particular is what is the foundation for ASCOT. And we use Snaptron to develop de novo algorithms to identify these cryptic splice junctions without any reference annotation. And the best way to understand what Snaptron is, you could envision a giant table or matrix where every row is a splice junction, all recorded splice junctions, and every column is every publicly available data set across the public archive. And essentially you populate this gigantic table, and Snaptron enables very rapid querying of this gigantic database. So you could envision that when we have cryptic exons, we can look for targeted approaches instead of having to rely on these very complex analyses and trying to build out the true representation of biological transcriptive complexity. We can focus instead on these binary splicing decisions and really narrow in on a targeted approach to look for cryptic exons in the public archive. And these inclusion junctions and exclusion junctions are simply rows within Snaptron. And once we know where to look, using ASCOT and other algorithms, we can determine what are the cryptic exons that are associated with disease and then query the public database. So here is an example of cryptic exons that we identified from the public archives. In the control data sets, we don't see this cryptic exon, which is labeled here in green. But when we knock down TDP-43, we activate it. These 6 data sets were pulled out from the public archives without prior knowledge. Now, this stressor, we aren't able to reveal what it is exactly yet. It's not entirely unexpected, but this is just a proof of concept where analyzing and identifying these junctions and looking into the public archives for the presence of these junctions revealed a previously unanticipated connection. And this is a very powerful technique because no one would have looked for this without the ability to massively parallel query all the data sets online. So that's, the strength of Snaptron and Recount 3 is really reducing the number of hours required to do these kinds of searches. Unexpectedly, we also find that other diseases such as cancer present with some cryptic exons as well. And we're still investigating this to better understand what are modulators for perhaps ALS and neurodegeneration, but also other human diseases. So again, this is another cryptic exon where in normal cells, there is no splicing event into this region. But when you knock down TDP-43, you activate this exon. This is actually quite a little bit of a complex case because there are 2 splice sites for the 3' side. But regardless, in certain cancer cells and cervical, liver, ovarian cancer, depending on knockdown of different splicing factors or other proteins, or even just activation of P53 with certain molecules, you get this activation of cryptic exons, which has thus far not been reported. So this leads to the question of, are these more common splicing abnormalities than we had previously anticipated? TDP-43 was only observed in neurodegeneration because of the clear pathological aggregate. But here in this case, the splice junctions are also just as obvious, but they have never been tested before, like we have had in pathology. So this represents kind of like a new novel way of looking across human disease. And it's all thanks to the accessibility of public sequencing databases. Likewise, when we knock down TDP-43, this is another exon that is only incorporated a little bit, but it's present in basically every case of TDP-43 knockdown, regardless of tissue or cell type. However, we find several data sets across the public archive that have no relation whatsoever to ALS or any neurodegenerative disease. And yet this cryptic exon is activated to much higher levels than we ever see with TDP-43 knockdown by itself. So clearly there's other biology that is regulating these exons, and we believe that a greater understanding of how these events are controlled will perhaps lead to a better understanding for how ALS and other TDP-43 associated diseases manifest. So I'd like to conclude with just this kind of summary of a conceptual framework where we can enter a loop that's purely computational in between experimental design. So I've been, classically trained as a biologist and a neuroscientist, but the power of splicing and the utility of these publicly available data sets really is going to, I think, really revolutionize how we approach experimental design in the future, because no one person can do all the experiments, but we leverage the collective effort of all experiments across the world. We may find insights that are truly novel and unexpected. So we can start with our first rational design, and we generate a list of potential cryptic exons. We take those cryptic exons and we query the sequencing archives and find previously unassociated data sets. Then we take those data sets and we can re-identify a new set of cryptic exons and then branch even further into the public query space. With several iterations of this, we can get a better sense of what's going on, perhaps design a second round of experiments and re-enter the wet lab space, I would say. And I think this this is going to be a powerful technique, at least for our lab and for other labs that can leverage sequencing databases. Now, there's going to be many other types of data sets out there in the future, but I just wanted to give this kind of example as to demonstrate the power of efforts like Snaptron2 and Recount3, which IDEAS has supported in the past and is currently hosting, I believe. So with that, I'd like to conclude and just thank all the members of the labs that we collaborate with and the funding bodies that have supported the work in the past.
Thank you very much. You're early. I didn't have to bother you.
Yeah, sorry, I tried to speed up because I thought we were running short on time, but didn't want to give some people a break.
Yeah, so that's a fascinating talk, and I think we have time for questions. Let me just start off with asking you about a comment you made early in your talk that ALS is part of a spectrum, which is kind of a recurrent theme nowadays in medicine, especially in, I think, neurological diseases where you find that a particular condition is part of a spectrum of other. Is that, I mean, do you think enough is being done to sort of look across the spectrum when you're doing research on these, or are people still sort of siloed in?
Well, I think it's only as good as our data. When we look at the pathology, we find that there are many, it's far more complex, just as cancer is, you know, there are many subtypes of cancer. Same thing happens with human disease, and there's neurodegeneration, and there are many overlaps between the different diseases. We find TDP-43 pathology in a variety of unexpected areas, and there are multi-system pathologies where patients present with multiple types of what are considered classical aggregates found only in like Parkinson's. But people, I think many common processes can lead to a similar common end result, and that's really what we need to do a better job of understanding. What are the upstream events that initiate these causes? And the data, really, we have to rely on end stage patient samples. But if we had, you know, more genomic data, for example, right, where it's more of a reflective of the upstream events, then perhaps we can, you know, form a bridge across the gap there. But yes, I think it's really just depends on how much data we have available to us to query and analyze.
And are there any unique challenges to working with public data, or is that actually?
it's very messy and can be quite non-standardized. Mm-hmm. But the strength of splicing is that it is internally controlled. In a sense, the ratio, we call it percent spliced in. Exons that are spliced in really are bounded by 0 to 100. And so when you look at a data set, the percent splicing is independent of the expression of the gene. So regardless of how many reads we get across that region, we can actually determine the percentage of utilization, you know, quite efficiently. And that's a very useful method. Plus this junction readout, where there's one segment in one part of the genome and then another segment in another part of the genome, that is a very reliable readout, and you know, we can distinguish from noise quite effectively. So this is why I've kind of leaned towards the splicing angle for many diseases, because of this reliability. Mm-hmm. But that's not always true for all data types. In fact, I would say this is actually far more commonly the exception to the rule. But you know, if we can find more similar data types like this, I think biology can really enter a new renaissance of effective analysis.
Oh, thank you. Any further questions for Dr. Ling? I don't think I'm seeing anything. Well, so we're less than 5 minutes behind schedule, so we will take our full 10-minute break now. Get back here on the maybe a couple minutes before 3 o'clock, or at 3. I think at 3 would make sense. All right, thanks everyone. We'll see you in a little bit.
Hi, Katie.
We're starting at 3, okay?
Yeah, yeah.
I'll be right back.
Yeah. So I think let's start. So the next speaker will be our own Katie Ramesh. So Katie has been running HEMI for quite a long time, and now he is the vice president for Johns Hopkins in charge of the AIX program. And he is going to talk to us about this amazing possibility and direction where the whole university is hopefully heading in the next few years. Katie, thank you very much.
Thank you, Alex. I should say up front, I'm not the vice president. So my role is simply senior advisor to President Daniels for AI. So let me share my screen here. Oops. Says I can't start screen share while the other participant is sharing. I guess Tara's going to have to stop sharing.
Sorry about that.
No worries.
There you go.
Let's see, this should work. All right. I hope you guys can see my screen here. Full screen. Okay. Tara, could you just confirm you're seeing a full screen view?
Yep, I can, and it looks great.
Great. All right. So my objective today is to just give you some big picture views of where we're going with AI at Hopkins in terms of an initiative that we have called the AIX initiative. We're in the early stages of this process, so there's a great deal I cannot talk about, but there's a good deal that I think I can talk about that will help us maybe come together a little bit. I'm going to focus on sort of the processes we've been using as we decide on what we want to do, some of the potential directions in which we might go, not thinking technically, but really big picture across the university, and maybe some priorities. So let me just run through this in pieces. So let me start with a graphic, which gives you a big sense of what we're trying to do. And recognize up front that I am not a graphic designer, right? So obviously at some point, somebody professional will come up with a nicer way of representing this. But the idea is that we will look across Hopkins, trying to bring the university together, where we look at the collaboration of humans and AI with respect to domains in which we have particular strength. And the particular focus areas for us will be obviously in the foundations, and then in health, safety, and discovery. Let me talk about what I mean by foundations for a minute. Actually, I should back up first and say what I mean by AI. So I'm going to, for the rest of this talk, describe AI in the largest sense possible. That is, I'm not going to try to be restrictive and limit the space. Rather, we're going to try to keep this expansive so that people across the institution who see particular ways in which they can use AI will see themselves within the space. So certainly it covers the traditional areas of machine learning and data science and expert systems and search and all of that stuff. Also would cover those areas where someone is simply using maybe an established technique in machine learning and then applying it into their particular discipline. We're going to let that all fall into the big bucket because our objective is to really accelerate everything that we do through this process. But given that, when we think about foundations, we're really talking about the mathematical, computational, computer science, and ethical foundations of AI. And then we think about the application domains that are outlined here, health and medicine, safety and assurance, perhaps security and assurance, although I'm not going to talk about security, and then discovery and inquiry, which covers pretty much everything that people at the university do. One thing to remember also as we spin up is whenever you talk about spinning something up inside an institution as big and as important as Hopkins is, you really have to think about how you do it. And we're going to see diversity, equity, and inclusion, which I will abbreviate as DEI, as foundational principles in what we do. That is, on two fronts, right? Obviously, any organization you have, you want to think about these as fundamental principles in how you run the organization. But there are a couple of bigger issues that are specific to the AI space that we need to think about. One is more than many technologies, the technologies that we spin up using what we're broadly calling AI here tend to have very large-scale impact on people. And that impact can lead to a great deal of iniquity if you're not careful. And so we're going to spend some time really thinking about what impact we have with the particular things that we choose to do. So we want to be intentional about the choices we make so that we maintain an equitable impact and improve the diversity of the population that we're looking at. Another side of it is that the community that develops AI tools right now is somewhat monocultural. And I think we need to expand the diversity of that community because in some sense, we are more likely to develop capabilities and technologies that will have equitable impact if the right people, if the appropriate people are then developing those, right? So if you don't have the right perspectives, if you don't have a broad range of perspectives, it's hard to develop tools that have a broad, that have equitable impact. So we're really going to think of this intentionally as we move forward. I'll talk about that in some more depth as we go. Our emphasis inside the university, and this is primarily an institutional program right now. I'm not talking about the science questions outside. I'm talking about this in terms of what we do at Hopkins. The idea is to build something that goes across the university. Now, those of you in the university, you know that we have a number of divisions, which we call schools. We've got 9 of them, right? Engineering, Krieger School of Arts and Sciences, medicine, applied physics lab, School of Public Health, Peabody, but a number of these divisions. And the idea here is this organization, this effort goes across all of those divisions. So we'll primarily spend our effort on investing in the bridges, in the things that bring us together as groups. The other side of that is that our divisions operate with very different business models. Those of you who are faculty, you know this issue that, the way in which engineering thinks as a school is different from the way in which the School of Arts and Sciences thinks as a school. And that has some consequences in terms of how business operates and how we as faculty, how we are able to do our work. So we'll have to be careful about that when we want to bridge across the schools. And part of that, which might be of interest to many of you, is this is going to mean that we will need new kinds of appointments for our faculty and technical staff, appointments that are significantly more flexible, both in terms of the structure of the appointment and potentially in terms of the structure of the compensation, so that we can do a wide range of different kinds of things and still see ourselves as core to Johns Hopkins in terms of our effort. All right. So staying at the big picture level, though, I'll just give you a quick sense of the kinds of people that have already been participating inside the AIX effort. It's a fairly broad range. I'm not going to try to read all of these to you, but you know, the first few bullets on the left there, those really come from medicine, then public health. APL, the Applied Physics Lab, is a big player in this space, actually a very big player. You can see physics and astronomy there, Alex's home department. Number of departments to engineering. This really goes across the whole university. And that's a point I want to make that's important. You know, there is a tendency for us who are the specialists in a field to view the field from within its specialization. But this is an area that has so much impact, we really have to look very broadly and bring all those perspectives in. So with that in mind, what we did in terms of process, and I'm going to spend some time talking about process first, is we've got a steering committee that looks at how we work, what kinds of things we should be thinking about, tries to integrate across the university, tries to identify potential points of conflict ahead of time, tries to identify potential opportunities so that we can then pursue them. And you can see the members of the steering committee here. So Alex is as the director of IDIES, you know him very well, he's here as well. A number of other folks that I'm sure you interact with. It's a fairly broad cross-section of the university, not designed to be the organizational leads, but more the intellectual leads who come together inside the space. Actually, I just realized my picture is not there. Got to be in there somewhere. Anyway, the way we actually operate with respect to this is we said, well, there are some issues that we need to think about that are important for the university to get a handle on, because it is a research institution that we're looking at. The first thing we think about is research and scholarship. So what are the things we should be doing with respect to research and scholarship in the AI space? And for each of these task groups that we organize, so in each area of interest, we organize a task group. Each of these task groups is a pair of co-leads, and then a large number of members. I'll show you some of those in a minute. But research and scholarship is sort of the largest activity you have at a research institution like this. And so this has had a great deal of interest and a great deal of activity that has ended up with some recommendations that we will move forward on. So I guess I should say this first. So the idea here, in terms of process, was we have the steering group, and then we created a variety of task groups looking at specific aspects of the issue. And we've asked each of these task groups to write a report based on their discussions with the broader faculty. And those reports then get collected and are presented to university leadership, which uses them to make decisions on exactly what we'll do within the initiative. So those reports at this point have already been developed in a draft form, have been presented to the provost, but there'll still be updates and modifications to these as we go. So I encourage people to continue to provide input so that we can improve where we are. But research and scholarship is the big thing, as you might expect. The second big thing is academics and training. René Vidal and Patricia Janak are the folks driving that. And they made a number of recommendations as well. Actually, just thinking about the time, I'm going to go ahead and start talking about some of the things that have come out of this without going into too much detail. So research and scholarship has suggested a number of directions that we should follow, a number of big picture initiatives that maybe we might want to think about. And in particular, they've also talked about how people should come together and how some of this work can occur most effectively. One of the ideas there is to identify a few demonstration projects that have an integrative character, that really have an application in mind and bring everyone together around a common vision, and to run those over the very long term. Academics and training has been looking at the entire cross-section of students and trainees that come to Hopkins. So starting from undergraduates through graduate students and postdocs and clinical fellows and trainees of various sorts. And one general idea here is we'd like anyone who comes to Hopkins to learn to have the opportunity to be exposed to AI and education in AI. We'd like AI to really be part of the fabric of a Johns Hopkins education. And it's really important here to recognize why we call this thing AIX. So the idea is not that we are focused just on AI as AI alone, but that we are interested in the intersection of AI with different domains, whether they're of discovery or of application. So for instance, you might be interested in the intersection of AI with anthropology, right? Or sociology, or perhaps it's AI as it relates to epidemics. All of these would fall into this category. Our interest is in the bridging between these. And as we think about the educational component, that's really where our focus will be. So we'll provide ways to bridge in terms of the education. At least that's one of the recommendations. There are multiple in there. We have a task group looking at external partnerships, whether we're talking about the large companies, the big tech companies that you all know, but also the little companies, the nonprofits, the other academic institutions that we interact with. What kinds of partnerships should we have? What are the ones that we should encourage? And how do we manage, particularly, the flow of data with respect to those partnerships? Infrastructure is obviously a big deal. This is run by Szalay and Paulette Clancy. They've made some recommendations as well about the computational infrastructure, the personnel infrastructure, and so forth. We incorporate all of that. A big area, as I mentioned a little while ago, is this whole question of impact. What kind of impact do you have in the AI space? And it turns out to be very significant. And so the question of how we assess that impact, how we assess the equity as a consequence of that impact, or the inequity that develops as a consequence, how we assess translational work that faculty members do. Right, if you're a faculty member who's primarily building tools as compared to doing pure science in a more traditional discovery context, how do we evaluate these things? All of those are being considered by that task group. And finally, there's a group that looks at organizational structures. How will this thing actually operate in the context of a large research university? And that's run by Scott Ziegler and myself. So these groups have gotten together and made some recommendations, continuing to get input, continuing to refine those recommendations as we go. Obviously, the university leadership is not bound by any of these recommendations, but the recommendations help inform what the university does. And I think the fact that the faculty at large have provided input is a really important way to build large-scale science directions inside a university. You can get a sense of some of the activity simply by going to this website, so ai.ghd.edu. This is currently not a website that we are advertising to the outside. It's primarily something we're using internally to get everyone on the same page to build our collaborations, but you can see the full membership of all the task groups as you look at that. I'll give you a quick list here, but I recommend you just go look at the task groups on the website, and you can see all of these people, and you can see pictures of these people, even better. But you'll get a sense of this. So research and scholarship has a wide range of folks in it, academics and training, and so forth. Actually, I'm just going to skip over these slides. The same data is on the website. Actually, more up-to-date data is on the website. So we'll skip this. All right. So with that kind of context, so we've had the steering group operating. We've had these task groups that have made recommendations. We continue to evolve those, and that information is moving up through the institution in terms of implementation. We'll get to that in a minute. I want to spend some time talking about diversity, equity, and inclusion, and in particular, how it applies in our space, in this AI space. Because to me, this is looking at this through the diversity and equity lens is a really important thing when we look at something that can have as much impact as we know we're likely to have in the space. So just a few things to recognize. One, obviously increasing diversity in the talent workforce that develops. That's going to be critical. That'll help drive innovation. Second, addressing the inequities up front will help us reduce disparate outcomes. So let's focus on that. And third, really looking at the ethics of AI in an inclusive environment. This is going to be important. And it's an area where this institution has particular strength in terms of a number of the ethical questions and the way in which we think about them. So this sort of general statement of things that are good for us. There are some specifics that come from that. And the way we think about that is we come up with some draft principles in the space. These principles will continue to evolve. But the idea is every time we make a decision on where to invest and what to invest in and what kinds of things to encourage, we ask the question, are we being consistent with these principles? And if we are, then we think it's a good direction to go. So this is the idea of defining your values and principles up front and then using them to assess the decision you make is something that's going to drive us. So obviously, the first bullet is just saying this is foundational. The second one is saying our emphasis is on looking at what the diversity is of what it means to be human. And if you're coming at this from the humanities perspective, you know what I mean. And if you're coming at this as an engineer, you say, what does it mean to say? What does it mean to be human? But part of what these technologies do is change what you do as a person, as an individual, how you think, how you work, how you interact with other folks. And we ought to spend some time thinking about how that works and whether we're doing this in a form that is what we think is in the best interests of the populations that we serve. A core part of the effort is enhancing the folks who actually work in the space. And we do expect that the translational impacts will have aspects of a big impact. So with that in mind, here are some expectations. So as a program, as an initiative, we'll consciously seek to enhance the inclusion of diverse identities, viewpoints, ideas within the development of the program and within our decision-making processes. This is not as easy as it sounds, right? It's easy to say it and it's harder to do it because we have built-in systemic things that you've got to be careful about, watch how they work, ensure that things are operating correctly. One thing we think about is what metrics should we use for assessing the biases inherent within the training data sets that we use. This is not straightforward. There's obviously a technical question of what the bias is, but there's also the question that's really a question that relates to the social side of this problem and the human side of the problem in terms of whether these data sets were developed from limited sets of the population, which subset was provided, how disaggregated is the data with respect to things like gender and race and so forth. So these are all things we need to think about. And we need some metrics for assessing what that is, even before we build out the tools. Similarly, we have to look at metrics for assessing the performance of what we built, right? And these, again, are non-trivial. We don't have good metrics for these things right now. And so we hope to work, one of the strengths of this institution is we cover the spread. We have folks in the humanities and social sciences, we have folks in the sciences and the engineering and medicine and public health in the applied physics lab. We can cover that spread and really be able to get a better handle on what metrics we should use in here. The things that we develop, the capabilities and tools that we develop, we'd like to have some way of comparing what they'd be with respect to where we are right now in terms of bias and outcome. Again, this is not something that we currently know how to do. We need to invest some effort in getting there. And then assessing the changes in equity that result. All right, I've spent enough time talking about that. Let me back up to sort of really big picture things. So here are some broad outlines of what we seek to do within the initiative. Obviously, as a university, the objective is to strengthen our scholarship in the core areas, to drive the foundations, and in the sectors, in the domains of application of interest to us. More broadly, let me say it this way. Research in an institution like ours generally grows organically. Faculty members sit down and say, well, right now I'm working on this, next year I'm going to work on that. And then we shift direction and we go off in directions based on the things that are exciting to us. And this is something that we should encourage. And so the organic growth of research is absolutely something that we should help with, and providing the capacity to accelerate the growth of those research directions is one thing we will look at. In addition, though, we will also look at things that might have great strategic value for the institution and for the world, and see how we can drive those by bringing things together in terms of long-term efforts that really ensure that we have consistent activity, consistent support over the long term, in addition to the research activity that we bring in from the outside, that as an institution, we provide support to ensure we can drive in the long term in some directions. And this is particularly of interest because you have to be able to maintain those data sets, develop them, and enhance the ability for all of us to access those data sets, something that you folks talk about routinely inside IDIES. A third component of that is enhancing the infrastructure. the compute infrastructure, the personnel infrastructure, the technical staff, the scientific staff, the high-level folks, right? The physical infrastructure, we do need to be able to sit together, work together, in addition to the electronic infrastructure that we have for our interactions, and to some degree, the administrative infrastructure. But the idea should be that we can bring people together, we choose a direction, an application domain, for an example, define a common vision, and then people can work together and they have the infrastructure behind them to do it. Now, this is somewhat non-trivial. I think our sense right now is that we are perhaps somewhat underinvested in this infrastructure, and we need to work on that. That fourth bullet there gives you a sense of scale. So our objective is to not just create these systems, but also implement them, deploy them, and then evaluate them. Now, Hopkins as an institution has a history of doing this, of taking ideas, implementing it, and deploying it. If you think about what public health does, right? This is basically what we've done. As an institution, we have a tradition of doing this. The question of doing it in this particular space means that we need specific things we need to build out. But one of our big strengths is the fact that we have the spectrum of divisions that have the capacity, right? So in the applied physics lab, for instance, we absolutely have the capacity to implement and deploy at scale. The question is, how do we bring these things together? But we will focus on giving us the ability to do all four of those things. And obviously that last part is an internal part. We really need to work hard to bridge across the divisions in terms of the business models that we currently have. All right, with that, let me close with a couple of simple thoughts. So in terms of just looking at everyone, well, I can't see anybody in the room, but for those folks who are listening in, if you ask the question, how can we help? And I'm going to talk specifically right now to the folks at Hopkins and looking at this. The first thing I'd ask is that if you're interested in this space, come register with us at this link on the website. That helps us build community. One of the things we learned very early on is we have a very large number of people who work on AI, and if you broaden this to say who just use machine learning, it's a huge group, right? And that we often don't know who is working in these spaces, and often on very similar problems. So there really is an opportunity here for us to come together and leverage the activity that we currently have. Second, it would be really useful to know what your needs are in the space. So given that initiative is underway, that we're thinking about what we should do, if there are specific things that you think we should be doing, if you could get that information to anyone that I mentioned in the earlier task group leadership or on the steering committee, or just send it to me, that would be very useful. It will give us ideas and directions on which way to go. Third, as this group certainly knows, these trusted legacy data sets are at the heart of modern AI. And the question is, what do we have? Who's managing them? How are they maintained? What opportunities do we have for enhancing them? How do we ensure that we can do this for the long term? What are the roadblocks in the way of doing that? Or what are the current constraints that people have? Can we resolve those constraints? We also have a couple of committees I'd like you to talk to. There's a colloquium committee, Jeremiah Solom, Corbin Rivera, and Deborah Matthews, who are trying to build some community activities. They're making some recommendations right now. And then there's a website committee, that's Brice Menard and Stuart Ray and Alan Yule. And I'm sure they'll be happy to take recommendations on things we should do as far as the website is concerned. We are not announcing to the outside world yet. We will get there relatively soon. But at this stage, we're making sure that our ducks are lined up inside. So here's a summary of where we are now. We've defined some of the major structural and intellectual elements of the initiative. Those elements have come together to define a business plan, which we've laid out over a 10-year kind of window. That business plan is still being developed. It still needs lots of discussion among the different divisions. We are a highly decentralized institution, so we have to figure out how all of these pieces will come together. So just ensuring that we have alignment between the key stakeholders and key divisions inside the space, that really will help us with respect to our long-term effort. And then we're working also on the HR side to think about specific kinds of appointments, specific kinds of structures, the things that will make it easier for us to work together. All right, with that, I will stop, and I'm happy to take questions or comments if Alex or Tara said there's time for it.
So please type in your questions into the question and answer or the chat. So thank you very much, Katie, for the wonderful review of the ongoing effort. And so maybe if you can say a few words, just that roughly what is the approximate timescale on which we can expect you hear kind of an official announcement?
Yeah, so I think there are probably two timescales here. One is sort of an announcement of the intentions, and maybe with a separate announcement might be on the actual scale of the effort in terms of money. I think that second announcement is probably a little way further off. But I think an announcement in the next, I would say certainly within this semester, I hope, that will give us a sense of the pieces that are engaged without talking too much about the amount of money that's involved.
Yeah,
I would expect that very soon.
Yeah. There is another question from Jaime. So are there plans to partner with NSF and their AI initiatives?
Absolutely, Jaime. So we actually have currently, you probably know, there's an NSF call for AI research institutes that has just come out. Preliminary proposals are due January 15th or something, if you haven't already started working on it. And we will try to drive in that direction. There's a Google Doc that has been put together for people inside Hopkins. If you have an interest in this space, you can go in and sign up and say what you're interested in. And there are particular folks who are trying to lead efforts. There are 6 teams. Team 6 actually, which is on education, has 2 parts, part A and B. So there are 7 potential institutes that NSF will stand up. Some of those teams are directly in line with things that Hopkins has particular strength in. Trustworthy AI is one, neural and cognitive aspects with respect to AI is another, decision making is a third, a number of places where we have some real strength. And so I certainly hope that our colleagues will put together some strong proposals there.
Thank you. So if there are there any other questions? Yeah, I don't see any. So once again, thank you very much, Katie.
Thank you all
for giving us all an overview of this. I believe the word is Paulette. So.
Actually, Alex, I see there's one question in the chat, if I can take a quick minute to answer.
Oh, yes, please do. Please go ahead.
So, Ahmed, that is a very good point, and it's something that we absolutely are thinking about, and that is part of the initiative here to look at that. So, one of the key ideas or one of the key points here that you bring up is there a well-defined career path for someone in the AI space at Hopkins who is not a faculty member? If you're a faculty member, we know what those career paths are. If you're not a faculty member, what's a career path? And that's something that there have been a number of recommendations to work on that. I expect that we'll provide some, let's say, resolution of currently some diverse paths that are there into something that is a little more consistent across the schools. So that whether you're in public health or in medicine or in engineering, you will have a path that you can see running through the institution. And also building a larger community of those folks who are not faculty but who are operating in the space is really important to us. So yes, we will spend some time on that.
Yeah, thank you very much. So Paulette.
Thank you. Good afternoon, everybody. It's a great pleasure for me to be asked to introduce the winners of the inaugural Mark Robbins prizes. So let me give you a little bit of a background on Mark and on the prizes and a little bit on the winners too. So the Mark Robbins Prize was set up last year in order to recognize people with contributions that were outstanding in high performance computing, which, as KT mentioned, high performance computing has a huge cadre of people who are engaged in this and is one of Hopkins' strengths. So this prize is in honor of, unfortunately, somebody who left us in 2020, Mark Robbins. He was a professor in the Department of Physics and Astronomy from 1986. And he was not only a well-renowned physicist in condensed matter, but also he played an enormous role in terms of service in his leadership of what was then MARCI, the Maryland Advanced Research Computing Center. So after his death in 2020, we wanted to memorialize his contributions to high performance computing by setting up a prize to reward those younger people who are following in the large footprints that he has left. So the Mark Robbins Prize was set to reward students who were within 6 months of their PhD defense, and those who had made a substantial record of accomplishments in high performance computing and of using what was then the MARCI facilities, now ARCH, the Advanced Research Computing at Hopkins. And this year we focused on research quality and creative contributions to high performance computing, as well as service to their research group or the department or just the broader Whiting School and Krieger and other communities through their teaching, outreach, or other kinds of connections to the broader community. And I'm delighted to say that we picked 3 winners. And interestingly, they're in very different areas and in different departments. So the first one is the prize for the Future Faculty Award. And this is one given to a person who intends to follow, like Mark Robbins did himself, along an academic pathway, is currently a postdoc, and is again making a great contribution to high performance computing. And this award actually also carries with it an allocation of computational resources that are just for them and not necessarily for their advisor, but really for themselves to start that process of gaining some independence in terms of research ideas. And the winner this year is Dr. Pooja Mahajan. And it's especially great for me to get the chance to mention her name because I knew her when she was a graduate student, and it's incredible to see how she has progressed since then. She's going to be talking to you about deep learning models for target-specific antibody design. So that's sort of speaking to the very large prominence of Hopkins in the biomedical area. We have 2 awardees among the graduate student prizes, those who are close to defending. The first one of those is Karthik Menon, who is going to give us talk about computational and data-driven analysis of aeroelastic flutter. And so you're going to see something that's very different to Dr. Mahajan's talk. And the third person I want to mention, who unfortunately couldn't be with us as he's graduated and now has a paying job, or a real paying job, and that is now Dr. Andrew Ruttinger, whose work focused on renewable energy sources. And you've seen in the new Rosie Center that's been started that this is an area to which Hopkins aspires to make a big contribution. So we have 3 wonderful winners, 2 of whom you're going to hear from today. And so it's my great pleasure to start that off by asking Dr. Mahajan to talk to us today about her work. Thank you.
Hey, Paulette. So unfortunately, Sai's not logged on yet, but we do have Karthik here if he doesn't mind kind of jumping, going in first, and then I'll see if I can get Sai online.
Okay, thank you. Karthik, you're going to lead us off for the graduate student winners.
Yeah, I can jump in. Give me a second, please.
Aha, we see you.
Yeah, I'm just going to share my screen. Can you see my screen?
Yes.
All right, great. So, hi everyone. My name is Karthik Menon. I was a PhD student at Hopkins, and I'm now a postdoc at Stanford. I'm going to be talking about some work from my PhD on computation and data-driven analysis of aeroelastic flutter. Let me start off by introducing aeroelastic flutter, or flow-induced oscillations as it's more generally known. Flow-induced oscillations are essentially, to put it simply, self-excited oscillations of a flexible body caused by the influence of a fluid flow over the body. What it looks like in practice is, in many situations, like these animations on the right, where what we're specifically interested in is the flutter of aircraft wings, which you can see in these top two animations here. So aeroelastic flutter of wings is an issue that has very widespread applications. It affects all types of aircraft, from large transport aircrafts to very small aircrafts. It's sort of a limiting factor in the design of aircraft wings, because there are regulations regarding how fast an aircraft can fly based on how much the wings are going to oscillate. Also, with this recent thrust towards fuel efficiency and lighter structures, these wings are more susceptible to flutter, so it's becoming more of an important problem. But also, flutter is important in other fields of engineering, such as civil engineering. You can see down here that it affects these kind of civil engineering structures because of strong winds. It's also a possible source of energy extraction, which there are some research groups that are working on. For instance, this animation here shows these oscillating cylinders and these cylinders are oscillating because of the influence of this water flowing over them. And you can extract energy from these oscillations. So this problem of flow-induced oscillations is a coupled fluid structure interaction problem. What that essentially means is that if there's a flow over an elastic body, it induces loads in the body, that those loads interact with the structural properties of the body, which then makes the structure move, and that feeds back into the fluid dynamics. And so it's sort of a fully coupled system, which leads to very complex dynamics. A simple proxy that we use in my research to study flow-induced oscillations, a system that looks something like this, where I have a wing that I'm interested in studying the oscillations of. And this wing is placed in some free stream flow, and the flow velocity is being labeled as u infinity here. And the elasticity of this wing is being modeled using these springs. So there's a torsional spring here to model the pitching of the wing. And there's this extensional spring here to model the heaving or the up and down motion of the wing. In this talk, I'm primarily going to talk about pitching oscillations. So I'm only going to focus on this torsional spring. So we model the fluid using the incompressible Navier-Stokes equations, which here I've written in non-dimensional form, use the fluid velocity. And the dynamics of the structure, or the wing in this case, is given by this spring mass damper system, which this equation here is non-dimensionalized using the same variables that are being used to non-dimensionalize the fluid equations for them to be consistent. And if I just group each of these terms together, here you see in this equation down here that this is indeed a spring mass damper system, where this is the moment of inertia, this is the damping term, and this is the stiffness, and this torsional spring is being driven by the coefficient of moment on the wing. A couple of non-dimensional parameters that I'm going to talk about quite a bit in this talk are the reduced velocity, which is defined up here. Essentially, what the reduced velocity is a inverse spring stiffness. So when I say I'm increasing my reduced velocity. As you can see, the spring stiffness in the denominator here. So what I really mean is that I'm going towards a softer spring. And something else that I'll talk about is the oscillation frequency, which I'm just non-dimensionalizing this way. The way we solve this coupled fluid structure interaction problem is using a sharp interface immersed boundary method, and our code is labeled VCAR3D. But essentially what this allows us to do is we have a Cartesian grid on which the fluid equations are solved, and we immerse a body of any arbitrary shape into this Cartesian grid. So our grid doesn't really need to conform to the shape of the body, and this allows us to simulate bodies of different shapes with arbitrary motion, large amplitude or small amplitude motion, and it's very robust. The way this works is we use a ghost cell methodology, where essentially if this, in this image up here, if this, there you can see the Cartesian grid, and if this red curve here is the surface of the body, we impose boundary conditions by dropping normals from each point in the Cartesian grid to the surface of the body, and we use ghost cells to implement boundary conditions. And the surface of the body is tracked using Lagrangian marker points. So I'm going to dive straight into some results, and let's first look at what the system looks like. So here I have 3 different airfoils, or 3 different wing sections sitting at 3 different angles of attack. And each of them has the same U star or the same spring stiffness. And now I start allowing a fluid to flow over these bodies, and they start to oscillate, as you can see. The blue and red that you're looking at are contours of vorticity in the flow field. And as you can see, there are these large vortices that are being generated, and the amplitude of the oscillation keeps increasing. And you can now plot what is the maximum amplitude of oscillation against the reduced velocity, or U star, that I mentioned earlier. As I said, the increasing U star essentially means I'm going towards a softer spring. So as you go towards a softer spring, there's this sudden increase in amplitude, and then the amplitude starts to increase because spring starts to get softer, which is expected. Now, if I plot this for different equilibrium angles of attack, or different angles of attack at which the system started, you get these different curves where the bifurcation to finite amplitude oscillations happens at different different values of U star or different spring stiffnesses. And as they reach large amplitude oscillations, sort of the memory of the initial condition disappears. So there's already some questions about why the start of the oscillation happens in different U stars, and those are things that we explored in some of my research. But something else that I'm going to show here is, so we were interested in looking at what's the effect of different parameters, one of which is the elastic axis and the other is structural damping. The elastic axis is essentially the point on the airfoil about which it's pitching. So for instance, this airfoil here is pitching about 50% of the chord. So I'm going to say the elastic axis is 0.5. And here I'm plotting what is the amplitude of oscillation against U star for 2 different values of structural damping. The red curve here is non-zero structural damping, and the black curve is zero structural damping. As you can see, with zero damping, the oscillation amplitude is higher, but also the nature of the bifurcation changes. So that's something interesting that we noticed. Now, something that we found very curious is that if you now change the point about which the airfoil is oscillating to 33% of the chord, so now the airfoil is oscillating about this point here, you get completely different behavior, where as you increase U star, which as I said, you're going towards a softer spring, you get an increase in amplitude of oscillation as you expect. But at some further increase in U star, where you go towards a very soft spring, the amplitude of oscillation actually drops, which is completely counterintuitive. You would usually expect that as you have a more flexible body, the oscillation amplitude has to keep increasing. So we are wondering, is there a nice way to understand how the amplitude of flutter is determined? And to do that, we developed an energy-based analysis technique. So if we take this spring mass damper system that we started with, we can convert it to an energy equation here. And with some assumptions, we actually can convert that to this discrete map here, where A theta is the amplitude of oscillation at any given cycle. And the amplitude of oscillation at any given cycle equals the amplitude of oscillation of the previous cycle, plus this term here, which primarily depends on E star, which is the energy extracted from the flow. So the energy extracted from the flow essentially comes from the work done by the coefficient of moment on the airfoil. minus losses to damping. Then the nice thing about this equation is that it gives us this analytical form for what the amplitude growth is supposed to be like between cycles, and that depends purely on this energy. And because we have this nice analytical form, we can also say nice things about what the stability criteria are and what the equilibrium criteria are and things like that. So the system reaches a stable equilibrium when there's zero energy being extracted, and this gradient of energy with respect to amplitude is less than zero. But the question in all of this is, sure, we have this nice equation and all that, but to be able to actually say anything about the system, we need to know what this energy extraction is as a function of kinematics of the body, because we can't a priori predict what the coefficient of movement is for a certain kind of pitching amplitude and frequency. So what we went ahead and did was we developed this idea of energy maps. We developed this idea of energy maps where essentially we did this large scale study of about hundreds of simulations where in this case we're actually forcing the airfoil to oscillate with a particular amplitude and frequency. So this is not two-way coupled, we're telling the airfoil you're going to oscillate this particular frequency and amplitude, and for each of those systems we calculate an energy of extraction because we have all of these quantities for each of those systems. And using that, we map out what the energy extraction landscape looks like. So here, this is an example of an energy map where I'm plotting in contours of energy extraction as a function of oscillation amplitude and oscillation frequency. These dashed lines here are the contour of zero energy extraction. So these are the equilibrium regions for this system. And so flow-induced oscillation can only exist in these red regions here, where the body actually extracts positive energy from the flow. And you see that firstly, this equilibrium region is really, really complicated. So it has a very complicated topology. And the first question we wanted to ask is, okay, now we have this energy landscape for the system, which we've determined using forced oscillations or prescribed oscillations. Does it actually correspond to what we're seeing in the flow-induced oscillations results that I spoke about before? So here I have the plot that I spoke about in the previous slide, where I have oscillation amplitude versus U star, and in this case, the oscillation amplitude increases and then decreases in this counterintuitive manner. And I can now map each of these points, because each of them has a fixed frequency and amplitude, onto this frequency and amplitude space on the energy map. And if I do that, it turns out that all of these points actually do lie on equilibrium regions, and they in general lie on stable equilibria, which validates the fact that this energy map actually tells us how the flow-induced oscillation system is going to behave. And the reason this is nice is because it gives, having this all of these bifurcations and the entire equilibrium space for the system allows you to also analyze why you have this counterintuitive behavior here. So essentially in this system, the reason we have this increase in amplitude and then decrease in amplitude is because as you're increasing U star, which in the frequency space is going from right to left, your system actually jumps up to this large amplitude branch here. And because of this emergence of another small amplitude branch here, the system gets stuck down there. And that's the reason you have this counterintuitive behavior. These energy maps allow us to now make predictions of what all the equilibrium states are, how the system is going to respond to perturbations, and many other things like that we can do based on now prescribed oscillations, instead of doing flow-induced oscillations, which are a lot more expensive and a lot harder to do depending on your computational method. So as an example of how this energy map allows us to now come up with control strategies, here's an example of controlling the gust response. So essentially what I do is I have an airfoil that is encountering a gust perturbation. And these dots here, or these circles here, show the trajectory of the amplitude growth of the system. So the system started at zero amplitude down here, and the gust actually pushed it up here, where it has positive energy extraction. And because it has positive energy extraction in all of these regions, the amplitude is going to keep growing and reaches its first stable equilibrium up here. So because of the gust, it starts to oscillate and shows like a 37-degree oscillation amplitude. But if you look at the energy map, you can ask, okay, what if I nudge the system into this region here where it has sort of a larger negative energy extraction region? And if I do that, in fact, I can control how much the oscillation response happens to be for the system. I go from something like a 37-degree oscillation amplitude to something like a 6-degree oscillation amplitude. And this all happens by just a slight change in the natural frequency of the system. So this is an example of how energy maps can be used to tune or to control oscillation responses. But the overarching question in all of this is, what drives this complex flow physics? As you can see, this topology of the energy map is very, very complicated. It's known in the fluid mechanics community that vortices, as you can see here, are responsible for inducing nonlinear loads and moments in immersed bodies. And these large number of vortices and these large vortex and these complex vortex interactions make these nonlinear forces and moments even harder to understand. And it turns out that the importance of these vortices isn't just a feature in aerodynamics or in traditional aerodynamics applications such as this. It's also a huge thing in a lot of other applications. For instance, in insect flight, it's been known that leading edge vortices, which I'm calling LEVs here, which are vortices that come off the leading edge of the wing, are known to generate extra lift. And that's one of the reasons that insects can fly at such a small size. Vortices are important for the opening and closing of heart valves and also for propulsion in many biological systems. So some other work that I'm not going to speak about here, in some other work, we showed that you can actually compute exactly how much force of all the force that's being induced on a body due to flow. You can compute how much of that is coming from specifically vortices using a specific mathematical formulation, and it gives you an integral such as this, where these here are quantities that depend on the kinematics of the system. And you integrate over some particular volume to get how much the vortices in that volume have affected the system. Now, the nice thing about this is if I pick the volume of a specific vortex, I can ask how much of this force is coming from each of these specific vortices. But the difficulty with something like this is that if you look at, for instance, these pictures up here of these vortex dynamics, being able to pick what is the volume of a specific vortex as it's interacting and as it's being shed and broken up and things like that is very complicated in these kind of flow fields. So we decided to take a data-driven analysis approach where we use a variety of data-driven techniques to analyze what the vortex dynamics are in various systems and to be able to actually dissect these systems on the basis of individual vortices. And I'm going to talk about two specific applications, two specific methods that we developed. One of them is this idea of identifying distinct regimes of vortex dynamics. So if I have a large ensemble of simulations, which, as I said before, in my energy map that I created to map out all of the equilibrium regions for the system, I had to do order 100 simulations. And amongst these order 100 simulations, you can have very different vortex dynamics, and they can all behave in very different ways. So the question is, can we identify distinct regimes within these large ensembles of simulations? And to do that, we developed a framework that essentially takes all of these simulations and extracts certain features that we care about. In this case, the feature that gave us the best results was just the time averaged vorticity field. So I take each of these simulations, I time average it, and look at what the time averaged vorticity field is. And then I can stack these feature vectors for all of these 100 or 200 simulations into a large feature vector space, which I then do a dimensionality reduction on, and then I can do clustering on the system where I find clusters of simulations that all behave the same way and have similar vortex dynamics. So the clustering method that I use for this particular case, and it's flexible, you can use different clustering methods, the method that I use is Gaussian mixture modeling, where the idea is if I have some clusters of data in for instance, in this case, two-dimensional space, you just fit Gaussians over this data, and you pick the number of Gaussians based on the number of clusters that you want. And each Gaussian corresponds to one cluster of data. Then the nice thing about this method is that it also allows non-isotropic Gaussians if you have covariance matrices that are that way. And so that if you don't know whether your clusters are isotropic beforehand, that's a nice thing. The way this works is if you have a data set in n dimensions where you have these capital N number of cases, as I said, you fix a set of k Gaussians over this, and you basically maximize the likelihood function to be able to do that fitting. In my case, here's what this looks like. So here I have an energy map. This is a slightly different energy map from what I showed before. This is it's an energy map for a system with different parameters. So as I said, this energy map is made up of doing many simulations at many different amplitudes and frequencies of oscillation. And this is what that grid of simulations looks like. Now I have 132 simulations in this case. And if I put it through this clustering procedure, it turns out that I get a certain number of clusters where within each cluster, the vortex dynamics behave similarly for all of the simulations. So just to illustrate that, here I'm plotting the time average vorticity field at the centroid of each of these clusters. As you can see, they all look fairly different. And the nice thing about this is now if I have like 100 or 200 simulations, I don't have to actually analyze what the vortex dynamics is in all of these 100, 200 simulations. I can actually just analyze the vortex dynamics at the centroid of each of these clusters. So now instead of analyzing 132 simulations in this particular case, I only have to analyze 10 simulations because I have 10 clusters. So that vastly reduces how complex your space is and how difficult it is to identify what is really happening in these flow fields. So this is really a way to take these global flow features and reduce them into a smaller space that's easier to analyze. Something else that we were interested in is now that we have these particular sets of the smaller set of simulations that represent the entire dynamics of the system, can I take each of these simulations and analyze them like at a more finer scale at the level of each individual vortex? So to do that, we developed another data-driven framework, which for each simulation, it takes in a time-resolved flow field. So here the time-resolved flow field is defined on a set of grid points. And what we want to be able to do is take all of these vortices that occur in this flow field and analyze each vortex separately in a variety of different ways that we're interested in. So first, what we do is we identify which parts of this flow field actually correspond to vortices, and we use this method called the Q criterion for that, which essentially is a method that's commonly used in fluid dynamics that identifies which part of a fluid flow is a vortex and which isn't. So here I'm just thresholding the flow field based on regions that are vortices. Now this is still defined on an Eulerian grid, or it's still defined on a Cartesian grid. And now to segment out each of these vortices as distinct regions, I do a density-based clustering on this grid. So as you can see here in this image, each cluster is now is identified by a separate label. So now I have the volume of each cluster, which is labeled separately, and here the colors represent separate labels. But the problem is, because this is time-resolved data and I'm doing this at every time step, these cluster labels change over time. So for each of these vortices, the color is changing over time. To be able to consistently label them, I then do a vortex tracking procedure, which is just based on the position of vortices between subsequent time steps. So now I'm consistently tracking each vortex as it's evolving throughout the flow field. The upshot of all of this is that at the end of that, the vortex identification and tracking framework, I have what is essentially the volume of every single vortex that existed in a flow field throughout its spatiotemporal evolution. So as you can see in this particular case, there are lots of vortices that are being shared. They're all interacting with each other, but I know exactly where each of them is going now throughout their spatiotemporal evolution. You can now study this in lots of different ways. For instance, you can study the kinematics of these vortices. Here I'm plotting just the trajectories of some subset of these vortices from the simulation. I can also plot other things for each of these vortices, like their circulation or their shape and deformation and things like that. Basically, lots of different kinematic quantities of interest that might inform the physics of the problem. Something else that you can do is, now that you have all of this data, is to group these into vortex types. So all of these vortices, for instance, up here are a certain kind of vortex called the leading edge vortex because they're coming off the leading edge of the wing. And I can also group another set of vortices into trailing edge vortices. And once you have these groups, you can compute ensemble averages for quantities of interest within each of these groups. But really what we're interested in this work is, as I said earlier, we developed a formulation to compute what the force due to a vertical region is, or what the moment due to a vertical region is. And that depended on the volume occupied by each vortex. Well, now because of this framework here, we have this data-driven framework gives us the volume occupied by every vortex throughout the spatiotemporal evolution. So now we can compute how much force has each vortex induced on this body. And so here, this is the coefficient of lift induced by two subsets of vortices. And here I'm just plotting ensemble averages of this coefficient of lift due to the leading edge and trailing edge vortices. So essentially what this framework allows us to do is it takes in a specific time resolved flow field, and it produces a quantitative analysis at the level of individual vortices, which gives us lots of information about these flows that are vortex dominated and where the vortices are the major part of the dynamics. It's also very flexible and it's automated, and it's easy to run on simulations that may be long or short or have different kinds of systems in them. As an example of how we can use this to now understand the dynamics of flutter, and tying it back to the idea of energy extraction and energy maps that I spoke about earlier, we can now ask the question, how much work does a specific vortex do to drive the flow-induced motion? So as I said earlier, the energy extracted by the airfoil from the flow is given by this. Now I can, instead of using the total coefficient of moment, I can use the coefficient of moment due to an individual vortex. And that gives us very nice information about how each vortex is affecting the system. So here, I'm showing an example for two cases. These have different frequencies of oscillation. The one on the left is a lower frequency, and the one on the right is a higher frequency. They have the same amplitude of oscillation. As you can see, so here I'm plotting the coefficient of moment due to specifically the leading edge vortex for each of these cases. And you can compare that with the motion of the airfoil itself, theta dot, which is just the pitching angular velocity of the airfoil. And you see that the phase of the leading edge vortex forcing versus the motion of the airfoil is different in these two cases. And that actually leads to very different energy extraction from the leading edge vortex. So in this case on the left, the leading edge vortex ends up doing positive work on the airfoil, whereas in this case on the left, the leading edge vortex ends up doing negative work on the airfoil. So when the leading edge vortex is doing positive work, you can say that it's actually enhancing flow-induced oscillations, whereas when it's doing negative work, it's diminishing flow-induced oscillations. So this data-driven framework, combined with the energy extraction ideas that I spoke about earlier, allows us to very nicely dissect what each part of the flow field is doing in driving flow-induced oscillations. So yeah, with that, I'd like to leave my summary and conclusions up here. Here are some references, and I'm happy to take questions if there are any. Thank you.
So actually, you have a little bit extra time if you want to go over your summary slide.
Okay. So anyway, so yeah, so this is just to summarize, we developed this idea of energy maps, where we have these energy maps allow us to, if you have an aeroelastic pitch oscillation system, which shows very complex dependence in parameters, which I showed earlier, because we have that non-intuitive, non-monotonic behavior in the amplitude of oscillation. The energy maps allow us to predict all the possible response branches and their stability within a certain range of parameters. And the way we do this is by doing a large number of prescribed oscillation simulations, which are much simpler than flow-induced oscillations or two-way coupled simulations. I showed that it also allows us to predict and control the nonlinear gust response of a system. And these control strategies basically depend on the topology of this energy map, because it tells you where all the stable regions are. We also developed some data-driven methods to understand the vortex dynamics of the system. Firstly, we used a clustering-based technique to understand what all the different vortex dynamic regimes are within a large ensemble of simulations. And this is useful for many different applications where you're doing a large parametric study. And after the large parametric study, you want to pick specific cases to analyze. You can use a clustering-based method like this. And the other framework data-driven framework that I spoke about is a physics-based and data-driven framework that takes a single flow simulation and dissects it based on the role of individual vortices in driving forces or driving the work done by the flow on oscillations. We're doing some future work in these areas. One is, so in this case, in the talk in the results that I just spoke about, I only spoke about pitching oscillations of an airfoil. The energy map idea can also be extended to multimodal oscillations where you have pitching plus heaving, for instance. It would just be a three-dimensional energy map instead of a two-dimensional energy map that I showed. Everything that I spoke about was for a simple two-dimensional system. And we're also trying to extend this to three-dimensional vortex-dominated flows. We're trying to apply these data-driven analysis techniques to flow fields from experiments. And we're also trying to extend this to aeroacoustics, where the pressure variations that are induced by vortices will also be responsible for acoustics of the system. So can we partition that and talk about how an individual vortex is responsible for a certain acoustic response? Yeah, these are some references, and yeah, so I'm happy to take questions. Thank you.
Thank you very much. I would invite people to put any questions in the chat. I'm not seeing any so far, but we have a couple of minutes. Okay. If there are no questions, then we can move on. Thank you very much for that talk, Karthik. It's an excellent.
Thank you.
Excellent talk. Thanks. So our next speaker is Dr. Pooja Mahajan. She got her PhD from Cornell University under the mentorship of Dr. Fernando Escobedo. She's been a member of Jeff Gray's group in ChemBE, and there she led the deep learning aspect of that group's research. And I actually don't have the title of your talks, so please go ahead and introduce it. And I think you have 20 minutes, and I'll give you a heads up at 15 minutes. There you go.
Hi, can you hear me?
Yes.
Thank you very much for this opportunity. I had prepared for a 30-minute talk, so I might have to skip a few slides.
Well, so maybe I'm wrong.
I'll just try to keep it short, but it's possible that it's a little hard to
I'll give you 25 minutes since we are a little ahead of time.
Okay, thank you. Thank you. The title of my talk is Towards Deep Learning Models for Target-Specific Antibody Design. And I'll just start. So antibody-based therapy is the basis of over 50 FDA-approved drugs. So antibodies are really important in therapeutic and biotechnological applications. Here I'm just showing a very small number of, just a subset of antibodies that have been approved by the FDA for diseases such as multiple sclerosis, various kinds of cancers, rheumatoid arthritis, etc. So what are antibodies? Antibodies are these Y-shaped proteins that are an important part of our immune system. And they have these variable regions at the tip of this Y that recognizes antigens, and these could be various pathogens, these could be targets on cells. And so they, in the immune system, these antibodies recognize and neutralize the antigen. So antibodies bind and neutralize antigens via 6 hypervariable loops. So at the tip of this antibody is the hypervariable region, which is primarily responsible for recognizing the antigen. And within this variable region, there are these 6 loop-like parts of the protein that recognize the antigen. So these are the loops that bind to the antigen and recognize it. These loops are called H1, H2, H3, and L1, L2, L3, and these are hypervariable in their sequence and structural space. And a common goal in antibody engineering for therapeutic and biotechnological applications is to generate library of antibodies that are enriched in antigen binders. And these could be for specific applications. So the antigen would be specific to the application. And when I say a library of binders, it means that these are libraries of antibodies with different amino acid sequences, and they primarily vary in the CDR loops. So similar to DNAs, which have bases A, T, G, and C, proteins and antibodies have amino acids as the building blocks, and there are 20 such amino acids. And so a library of antibodies would have different amino acid sequences. So typically, antibodies libraries that are enriched in binders are generated experimentally, and there are these high throughput experimental workflows to do this. So here I'll quickly show you how this is done in experiments. So usually in experiments, and these are wet lab experiments, they start with a single substitution design space, which means that if there are n positions on the antibody that you want to design, then they explore all 20 amino acids at these n positions using deep mutational scanning. They obtain this library of sequences, they express it, and then they carry out multiple rounds of screening for expression of these sequences to form stable folded proteins, and for binding to the antigen of interest. And following these multiple rounds, they can experimentally obtain this enriched single substitution design space. This single substitution design space can then be combined to form a combinatorial design space, and they do this experimentally. They allow all positions to be designed from this single substitution design space, and they can experimentally obtain a very large library of sequences. This is of the order of 10 to the power 2, 10 to the power 6 to 10 to the power 8. And then this library again is synthesized and expressed, and then it's further they carry out multiple rounds of experiments to enrich this library for protein expression. So these sequences should fold into proteins that can express stably, and for binding to antigens. And following multiple rounds of this process, they're able to obtain a subset of sequences that are now enriched for both expression and binding to the antigen of interest. And as you can imagine, this is a very time-consuming process, and it's also expensive. And the goal of my work is to develop fast deep learning-based methods to design large and inexpensive antibody libraries that are enriched in antigen binders computationally, without having to do the entire process experimentally. And we want to use deep learning models to do this because over the last few years or so, deep learning models have evolved tremendously, and they've revolutionized many fields, including image processing, speech recognition, machine translation, complex game playing, and more recently, the fields of protein structure prediction, protein design, sequence and structure generation as well. And so here I'll show you how we have developed a deep learning based framework to explore the combinatorial design sequence space for the CDR loops of antibodies, and then how we've enriched this design space for expression and binding to an antigen of interest. So here is just an outline of the talk. So over the last few years, many deep learning models have been proposed for protein design. And most of these models either rely on language-based sequence generation, similar to text generation for NLP, for natural language processing, or they use fixed backbone sequence generation with models that are trained for all proteins. So it's important to remember that antibody loop design is tricky. Loops are more flexible and solvent exposed, so methods that are developed for all proteins and more rigid secondary structural elements such as alpha helices or beta sheets may not be very effective for loop design. Also, arguably, language models may lack structural context, especially for CDR residues that bind to the antigen. And so we wanted to select a method that was more appropriate for designing loops. And so we have used the hallucination framework that was proposed by David Baker's lab earlier this year. So I'll go over this hallucination framework and explain how it can be used to generate sequences conditioned on structure. So hallucination is a framework that allows to use a pre-trained sequence to structure prediction deep learning model to design optimal sequences for a target structure. So what does this mean? So consider TR Rosetta, which is a sequence to structure prediction deep learning model, which means that given the amino acid sequence of a protein, this model can predict the three-dimensional structure. And so in the hallucination framework, you start with such a pre-trained model and then generate sequences that are conditioned on a target structure. I'll go in a little more detail to explain how the hallucination framework works. So let's say this is the structure of interest. This is the structure that you want to design sequences for. So you know the structure of the protein and you want to generate sequences that would fold into the structure. So first you express the structure. First you represent the structure as a distance map of distances between different residues. This is also the output of the TR Rosetta model. So at the same time, you start with a random sequence. You run it through the pre-trained TR Rosetta model, which then predicts a structure for this sequence. Now you calculate a loss with respect to your target structure, backpropagate this loss through the fixed TR Rosetta model, so the weights are not allowed to change. And then you calculate the gradient with respect to the input sequence. You convert this into a position-specific scoring matrix, which basically gives you a probability for the 20 amino acids at each position, which can then be converted into the sequence by taking the maximum probability at each position. This sequence is now passed again through the TR Rosetta model, which predicts a structure for the sequence. You again calculate the loss with respect to the target structure, backpropagate it, and a new sequence is obtained. And this is an iteratively until the loss with respect to the target structure becomes really small. And at this point, you've obtained a sequence that would fold into the structure, the target structure. And so using this hallucination framework, we want to generate CDR loops that are conditioned on the structure of the CDR loop. And we want, instead of using TR Rosetta, we have used the deep learning, the deep AV model that was developed for antibodies. So deep AV is the leading sequence to structure prediction deep learning model for antibodies. This is a model that's very similar to TR Rosetta. It takes in a sequence and then it predicts the structure represented as distances and orientations. And this model was developed only for antibodies. So this is very specific to antibodies, and compared to other state-of-the-art models, this model has very high accuracy on both the framework residues and the CDR regions of the antibody. And so using this model and the hallucination framework, we can basically generate loop sequences that are conditioned on a loop structure. However, there is no antigen present in this model. So neither TR Rosetta nor Deep AD have been designed for multiple genes, which means that there is no way to include the antigen in these hallucination runs. And so what we obtain out of hallucination is a library of antibody sequences that are conditioned on the structure, but they are antigen agnostic. And so we use a second step where we virtually screen this hallucinated library with another software that basically calculates the binding energy for the antigen of interest. And so by using these two steps, we can obtain a library of antibodies that are screened for the antigen of interest. And so this is the full hallucination pipeline where we use the hallucination framework to generate sequences that are conditioned on structure, followed by folding with deep AD that takes these sequences and then predicts the structure to make sure that the sequences hallucinated fold into the correct structure. This is followed by virtual antigen screening, and then we can do further, we can apply further filters to screen for other metrics that are important for downstream applications. And this whole pipeline takes anywhere from hours to days. And so this greatly cuts down the time that is required to obtain a library of antibodies that are enriched in binders. So to demonstrate this, framework, I'll show how we've applied this hallucination framework to generate a library of CDRH3 loops that retain backbone structure. And the data set that we've used is from Sai Reddy's lab at ETH. So, so in this data set, they have generated a very large library of CDRH3s that is able to retain binding to the HER2 antigen. And they go through multiple rounds of screening to obtain this library, and they're eventually able to generate a large library. A handful of these antibodies that are generated have an affinity that is similar to the wild type, and there is one antibody that has an affinity that is better than the wild type. Another interesting thing about this data set is that, so there are about 11,000 binders and non-binders in this data set. And if you look at the binding sequences and you compare it to the wild type sequence, you see that the binding sequences can deviate significantly from the wild type antibody sequence. This is very interesting because it suggests that binders are able to exhibit, binders exhibit high diversity in sequence space, and yet they're able to retain binding to the antigen. So this seems to suggest that diverse binding sequences must retain some structural similarity to the wild type CDRH3 backbone, and also perhaps retain the core binding motif. And this is perhaps not true for non-binders, which perhaps exhibit either largely different backbones or disrupt the important binding interactions. So based on this, we have two design goals. The first is to retain the backbone CDRH3 structure, and we can do this with our hallucination framework. And the second is to design without disrupting the core binding motif. And we've done this by running hallucination with some restricted sampling, where we restrict these two positions so that we retain the core binding motif with which the antibody recognizes the antigen. And so following this framework, we are able to obtain this library of hallucinated sequences. So these are all CDRH3 sequences that were obtained from restricted hallucination. And if I compare the restricted hallucination with unrestricted hallucination, you can clearly see that you're able to keep the sequences within this restricted space. There are other ways to fine-tune sample sequence space. So for example, here, I showed you how we can restrict the sampling using restricted hallucination, but we can also restrict the sampling to stay close to the wild type. So this is the hallucination library that we obtained by restricting the hallucination close to the wild type sequence. And so, so now if I compare the hallucinated library to the wild type, you can firstly see that similar to what they saw in experiments, hallucination samples a very diverse set of sequence space. And if we compare the restricted hallucinated library to the unrestricted hallucinated library, we see that the restricted hallucinated library is closer to the wild type than the unrestricted library. But more importantly, if we compare the hallucinated library to the binders and non-binders from experiments, we see that the hallucinated library shows overlap with these experimentally obtained sequences. So there is up to 80% similarity for some of the sequences that were obtained from hallucination with experiments. And even more interestingly, if we compare the hallucinated library that was restricted to sample close to the wild type, this overlap with experimental sequences increases to 90%. And if you look very closely, you can see that the distribution for that the overlap with binders of the hallucinated library is more than that with the non-binders. And that gives us the hope that maybe using hallucination, we can enrich sequences that are closer to binders than non-binders. So the next step is to forward fold the hallucinated sequences. And if you forward fold these hallucinated sequences with deep AB, here I'm showing the wild type structure in gray, and then the hallucinated structures that were folded with deep AB.
5 minutes.
Okay, in green. And you can see that the hallucinated loops are very close to the wild type loop. And this is also shown with the root mean square deviation of the hallucinated loops with respect to the wild type loop. So most of them stay within 2 angstroms of the wild type loop. We can also look more closely at the positions that we had restricted. So, and so here I'm showing the wild type amino acids in gray and the hallucinated amino acids in pink and magenta. And you can see that these stay close to the wild type positions, and therefore there is a chance that they retain the core binding motif. Then the next step is to screen this hallucinated library for antigen binding. And we do this by calculating the DDG using Rosetta. So DDG of binding, if it's more negative, it implies better binding to the antigen or higher affinity. And so if we look at the DDG and compare it to the wild type, we see that there are about 10% of the sequences that were hallucinated for the restricted library that have a DDG that is comparable or better than the wild type. And if we do the same thing for the library that was restricted to sample close to the wild type sequences, we can see that this percentage goes up and it's greater than 25% now. So this means that a significant percentage of the hallucinated sequences can at least in this virtual screening bind to the antigen. And this would you might suspect that these sequences are very close to the wild type, but if we look at these sequences more closely, so here at the bottom, I'm showing the logo of sequences that have an affinity comparable or higher than the wild type. You can see that there is a very large amount of diversity here. So we are not just sampling the wild type, we're sampling a rather diverse sequence space that can fold and also retain binding. And with this, I would like to summarize this work. So hallucination framework allows sampling of sequences conditioned on structure. We can additionally restrict sequences by introducing additional losses to optimize the objective. Hallucinated sequences with restricted sampling can retain binding motif, and then virtual screening through Rosetta or other methods allows for selection of binders. And then, so what's next? What is the outlook for antibody design? This is really interesting, but there are lots of other methods out there, and there are, so we need models that are more robust. So we use backpropagating gradients for input design in this case, which is not the most robust protocol. There, we also need models that include the antigen, and models that leverage known protein interface sequence structure data, which is absent from this framework, and other models that can capture more complex phenomena such as loop flexibility and induce conformational change upon binding. And so there's a lot happening in this field right now. This is a model that came out a couple of days ago. And so there is a lot more to be done in this field. And with this, I would like to acknowledge all the advisors and members of the Gray Lab and the other people who worked on the hallucination project with me, and also Marcy Rockfish and the Robbins Award for the generous allocation of GPU and CPU resources. And I'll be happy to take any questions.
Thank you very much. Let's see if there are any questions. In the meantime, so one of the things, I mean, you said that you're wondering whether it'll still be fast after you incorporate all these new effects.
Right.
Have you spent a lot of time making things fast up to now, or how difficult has that been?
So deep learning, so the benefit of many of these deep learning models is that at inference, these models are extremely fast. If you start including methods such as molecular dynamics or replica sampling, so there are methods that allow for large conformational sampling, and they are better at capturing large conformational changes. Those methods are slower, and you may not be able to look at analyze thousands of designs with them. So that would be one of the limitations of using other computational methods that are able to capture more complex phenomena, but they're not as fast. And then you would lose the benefit of using a computational model versus experiments. Experiments are still very expensive and take a lot longer, but not all computational models are as fast as some of the models that I've described today.
Great, thank you very much. I think that was a very interesting talk, and I think that concludes this session. I believe Poster Madness is next, and I'm supposed to hand it over to Jordan Raddick, I think.
Hi, everybody. It's great to see you all. Thanks for a great meeting so far. We're now going to do our Poster Madness session, followed by the poster session. So here's how it'll work. There are, I think, 8 poster presenters. They're all listed on the website. And we're all going to be talking one after the other to give a quick introduction to our posters. So that'll happen in just a couple minutes. And then we're going to go to the actual poster session. The poster session is taking place on a different Zoom meeting. The reason we're doing that is so that we can create breakout rooms and assign each poster presenter to one breakout room. And then you can join whichever breakout room you want jump from one to the other, see as many posters as you want to see. And within each breakout room, the poster will be displayed. The presenter will be there to answer your questions and to talk and just to learn about the kinds of exciting research that we do here at IDEAS. And David Albert just mentioned that the posters are on the IDEAS website. If you go to the symposium site, you can see the abstracts for the posters. So you can get an idea of which ones you would want to see. But another great way to get an idea of what to see is to listen to Poster Madness, which is going to start right now. Mac McComas is not able to make it, so I'll be presenting his poster for him. So I'll do the Poster Madness and then into the breakout room for Mac McComas's poster. So I will present that. I will present my own poster, and then we'll move in alphabetical order, starting with Arjun Agrawal. So before I start the Poster Madness, let me put into the chat the Zoom address for the poster session, which will begin as soon as Poster Madness ends. So don't click on this link just yet. Listen to us talking about our posters, and then click on this link, and you will go to the poster session, and you can join whichever breakout rooms you want to join. So I'm going to send this link to the chat, and then I'll start talking about this poster by Mac McComas about improving access to credit in majority Black neighborhoods. There's your link for the poster session. So Mac McComas works at the 21st Century Cities Initiative, is also a member of IDEAS, and I've worked with him on a couple of different projects. Haven't worked on this particular project, but I've worked on a closely related one. So the idea here is that there's an old cliche that says you have to have money to make money. And one of the best ways to get access to money in the US today is to get a loan from a bank or from a federal government program. And the way that banks give loans is very racially divided. It's a legacy of segregation in cities around the US, particularly in places like Baltimore. And so what Mac has done is to look at the options that are available for banking in various neighborhoods, particularly looking at traditional bank branches and what we call predatory lending agencies, short-term payday loans. And often when a bank location closes, one of these payday loans areas will open in exchange, and really with a profound negative effect on the community. So Mac is looking at these sorts of issues and how they play out in Black majority and white majority neighborhoods all over the country, and particularly here in Baltimore. So come to the Mac McComas breakout room. It'll actually be combined with my poster, which I'm going to talk about now. All right, so this is my poster, and it's much more of a speculative beginning research idea. I don't actually have a poster, but I do have a data set and some work that I've done on it. I want to start by telling you a story, and that is that my great uncle emigrated to the US from Montenegro at age 14, dropped out of school, came here, didn't speak a word of English, never did any more formal education. But when he got to the US, he discovered baseball and became a huge Cleveland Indians fan. And he never learned to read, but he taught himself how to read box scores and was obsessed with baseball statistics. And the reason I say this is that Uncle Marco wasn't somebody who would have traditionally been reached by data science outreach. And yet he had this love for data and for evidential reasoning and proving hypotheses and figuring out which baseball players were better and what the Indians' chances of winning were. I guess they're the Cleveland Guardians now, but they were the Indians back then. I have a data set that's currently on Kaggle and will soon be offered on SciServer that is events data from baseball. There's a lot of statistical data on baseball, but a lot of the really interesting questions are situational. What do you do with 2 outs, runner on third base against a left-handed pitcher? What kind of outcomes can you expect from that situation? That's the kind of data that I'm exploring through a website called retrosheet.org. The link to the data set is there, and I will hopefully see some of you in the poster session. So I'm going to join the other Zoom now, get everything set up, and I will hand it over to Arjun Agrawal.
Hello, everybody. My name is Arjun Agrawal, and today I'll be presenting my research on data science and analytics for esports. Esports, which is professional video gaming, has become increasingly popular throughout the world over the last 5 years. Like sports, there's a need for analytics in esports. Teams, bettors, media, and fans want efficient ways to evaluate these esports players, teams, and matches. Counter-Strike Global Offensive, also known as CSGO, is one of the most popular esports in the world, with over 40 million copies sold, yet it has lacking analytics. To this end, as part of my research with the New York University Visualization, Imaging, and Data Analysis Center, we introduced an analytics package that consists of 2 main parts. The first part is a leading edge generalized functions package that allows for the efficient filtering and aggregation of any data from any match. This gives users full autonomy over what data they want to access. But the second part of our analytics package is a specialized function subpackage, which allows for the efficient calculation of standard CSGO match statistics. Please come to my Zoom session to learn more about how data science and analytics are being applied in this emerging area of esports. Thank you.
Next up, we have Thomas Connolly. Thanks, Arjun.
All right. Hi, I'm Tom Connolly, and I'm an undergraduate at Carnegie Mellon. So my poster is about optimizing dynamic visualization techniques for the Poseidon ocean circulation simulation. So Poseidon is a full Earth ocean circulation simulation that is going to be run in the near future. And so the goal of this project was to develop a dynamic tile server visualization tool for the Poseidon data set. So this will allow for quick visualizations of the data without having to do any pre-processing on it. And this is achieved by using interpolator objects. So effectively for our tile server, each tile has an interpolator object which stores information about how the geometry of the tile corresponds to that of the original data set. So my poster is about how we can optimize these objects to allow for rapid and efficient image interpolation. So you can see some examples of the viewer tool that we've created in the right of the poster. And thank you. Come to the my session in the next Zoom room. Thank you.
All right, thanks, Tom.
Thanks, Tara. So I'm David Elbert, and the poster I have today that we're going to present is from a large group who've been working on this revolution really in materials science. So materials science and engineering is trying to use data-centric methods in particular to really transformatively accelerate the way that we discover, develop, and deploy new materials to meet a host of societal needs. And so this is entitled OpenMSI, a materials semantic infrastructure for streaming data integration in accelerated materials development. It's part of an NSF program called DIMREF, Designing Materials to Revolutionize and Engineer Our Future. And the idea is to interact with materials data in ways that really transition and change how we do the science that creates all these wonderful new materials like new superconductors or new stronger and lighter materials. Our instantiation has to do with creating a new, more spall-resistant aluminum alloy. But what we're really focused on is using Apache Kafka, building out a streaming infrastructure to capture the data, and then in real time, or at least much faster than previously, give feedback on these really incredible experiments and put that in a context. So we're going to actually show an example of that using OpenMSI Python, which Maggie Emmenizer here in IDS has been developing with us. And we host things here in IDIES. And at the bottom, what you'll see is we'll walk you through how an experiment works in real time when we do laser shock. So we take a high-powered laser in the laboratory, actually KT Ramesh, who presented earlier today. It's his laboratory and postdoc and graduate student that we're working with in this instantiation to actually impact, drive a microflyer foil at incredible pressures into the actual sample of aluminum to induce spall, and then how we can stream that data and then analyze, consume, and use that data and spit information back automatically so we can start working towards high throughput experimentation. So hopefully you'll come out, see the poster, and we'd love to discuss it with you. Thanks.
Thanks, David. Great. Carrie's up next.
Hi, I'm Carrie. I'm a grad student here in the astronomy department at Hopkins. My poster is about a new technique that we devised to identify candidate member stars of nearby dwarf galaxies using only publicly available data from large surveys. One of the goals of this technique is to try to find candidate member stars far from the center of their host galaxies. These stars can tell us a lot of different and interesting things about their host galaxies, such as its total mass and current dynamical state. However, it's inherently difficult to find member stars far from the center of their host galaxy, as the stellar density of a galaxy decreases as a function of distance from its center. So, once you get to the outskirts, it's kind of like looking for a needle in the haystack, where your dwarf galaxy member stars are needles and Milky Way stars are the hay. For this work, we looked for a specific kind of star called a blue horizontal branch star, because these stars have a unique combination of high temperature and low surface gravity, which means that we can use the filters of the Pan-STARRS publicly available survey to disentangle and identify these stars. So we used a k-nearest neighbors classifier to identify likely horizontal branch stars in the Pan-STARRS data. For a patch of sky centered on a dwarf galaxy, we then used Gaia data, which is another public survey. But this survey provides information about the motion of stars. And we use this data to try to determine which of the blue horizontal branch stars that we find are likely members of the chosen dwarf galaxy. We applied this technique to the nearby ultra-faint dwarf galaxy Bootes 1. We found candidate members at large projected distances from the center of the galaxy, and in a distribution that sort of hints that the system might actually be disrupting due to the gravity of the Milky Way, which you can see in this figure here. So I hope you stop by. Thanks.
Great. Thanks, Carrie. Peter's up next.
Hello, can you hear my voice?
Yep.
Okay. Hi, I'm Peter. I'm a student and or a PhD student in the Johns Hopkins University, and I'm also working with the Applied Physics Lab at Johns Hopkins. So my project is all about optimizing line of sight coverage. There are a couple ways where it can be used, where you could look at line of sight from cell towers for coverage, or you can look at it from a security standpoint and find line of sight from cameras. But a problem with line of sight in the past is it hasn't scaled very well with the land area and resolution of the terrain. So when we want to optimize the line of sight coverage, it can be a bit expensive to work with elevation and line of sight data. So so this is split up into 3 parts. The first was completed, but it was calculating line of sight from multiple sources like sensors or towers in parallel by tallying the terrain data and grouping the sensors together in a way that made it more efficient to calculate with a GPU. So that allowed us to handle line of sight of more sources more quickly. Then the second part was finding a suitable way to evaluate the entire laydown of line of sight sources, so that we wanted to effectively grade how many areas that you could protect with the line of sight cameras or needed coverage with cell towers. And then the third part is ongoing, but it's going to be optimizing the tower locations to produce the best scores and have the best line of sight coverage. And we're going to explore using Bayesian optimization for that path so that it'll minimize the number of expensive evaluations needed to give better and better recommendations for tower locations. All right, thanks.
Thanks, Peter. All right, I believe Visca is up next, yes.
Hi, my name is Visca Wei. I'm a PhD student at Johns Hopkins working with Lateral, Carey, Professor Budari, Professor Weiss, and Professor Szalay. I'll be presenting our work on physics-informed machine learning. So modern machine learning has become increasingly important in science. We collect increasingly larger amounts of experimental data, but our ability to analyze this data has not kept up with the data avalanche. Machine learning, in particular, variants of deep learning are emerging as a promising way to overcome this barrier. However, in science, we need to understand and estimate the statistical significance of our derived results. And there is a general skepticism towards black box techniques. For data with large dimensions, the networks can get quite large, making training slow and cumbersome. As a result, serious attention is being given to the physics-informed machine learning, how we can use prior knowledge about underlying symmetries, geometry, and the physical properties of the data to simplify network design. So our research is geared towards designing tools for the next generation AI telescope powered by deep learning techniques, augmented with insights from astrophysics, computer science, and artificial intelligence, during which we develop a physics-informed hierarchical scheme to estimate astrophysical parameters for stellar spectra. Instead of training a gigantic neural net that can work for all the spectra in parameter space, we use physics to break down the task into several small and simple problems. In details, we first subdivide the stellar spectra into distinct boxes based on their physical parameters using deep learning. And within each box, we then use a sparse embedding through the principal component pursues as a preprocessor to neural nets. In such way, we can perform locally optimized analysis of the physical parameters of the stars, enabling smaller networks and higher accuracy. Please read our poster for more detail. Thanks.
Thanks, Visca. All right. And rounding out our poster madness is Brian Wen.
Hi, hello everyone. My name is Brian. I'm an undergrad student at Johns Hopkins University. And my poster is going to be very much related to Thomas Connolly's poster earlier. Essentially, they're part of the same project. So again, our goal is to construct a large-scale visualization interface for global oceanographic data. And in my poster, I'm going to go over briefly the fundamental method that we use for data visualization, which is something called the barocentric interpolation model. Essentially, what this does is that we can compute image points on a uniform regular pixel grid, given data on sort of an irregular grid like the LLC 4320 grid. So with this model, we can visualize data at an arbitrary zoom level and an arbitrary image size. So we can, on the interface that hopefully you'll see later in our breakout room, we can zoom in as much as we want up to a certain level. And this allows very fast computation of the data points at sort of these zoom levels. So yeah, hopefully you can stop by my poster session later.
All right, great. Thanks, Brian. All right, and then again, the link to the poster session meeting is in the chat box. It's also here, but thank you so much for joining us for our first day. We hope to see you all back tomorrow. And yeah, please make sure you stop by and see the poster authors. Thank you.